So let us start on with the foundations of natural language processing. And this is the broad agenda of what we will see in terms of basic NLP. We will understand some basic NLP. What is it? How is it different from the types of problems that we have solved so far? Because all of what we have seen until now, we have focused primarily on structured data, data in tabular format, data in rows and columns. We will understand the terms that are tokenization, vectorization. We will see that. We will look at what is the different types of pre-processing techniques. How do we pre-process and do data cleaning when it comes to text data? We'll build some intuition around that. And then we'll also get into a very, very powerful technique called word-to-vec embeddings. What are word vectors and what are embeddings? So that is the other aspect that we will talk about. So this is just to list out the general agenda, what we will be covering with respect to basic natural language processing. Now, I'm going to take an example for all of you to explain the process, how it's happening. So let's say we have a text. Let's say we have a text, Hyderabad is the capital of Telangana. This is the text that I'm giving you. Now, one very important thing that you have to keep in mind is machines cannot understand text data. Machines can only understand numbers. Even if you have categorical data, if you remember our discussion from the first day when I was covering these topics, I mentioned something very similar. I told you that time as well that machines cannot work with categories. Machines cannot work with strings. Machines can only work with numbers. Machines can only work with numeric data. If you have something which is in a categorical format, if you have something which is a string type of data, a category, let's say city name, you have to make it a point to convert that to a number. And we talked about techniques like one-hot encoding, label encoding, if you recall. The same idea applies for strings also. If you have a string, machines cannot understand strings because behind the scenes, all the different machine learning algorithms, they are all working based on some kind of mathematical equations at a very high level. And there is some kind of loss functions, there is some kind of optimization we are doing, right? So there is some kind of math that is going on behind the scenes inside NumPy arrays. There are mathematical arrays inside which math operations are happening. So naturally, you cannot work with text data. You cannot work with string data. There has to be some inherent ability to convert this into numbers. How is that happening? Let us see that. Let us learn that. So the very first thing that we do is we take the entire text. In this case, Hyderabad is the capital of Telangana. We take the whole text data and we perform a process that refers to as tokenization. What is tokenization? Tokenization is the process where you take the entire text data. So tokenization is the process where you take the entire text data and we convert the entire text data into numbers. That is what we refer to as tokenization. So tokenization is the process where we take the entire text data and we convert the text data into numbers, into unique tokens. I'm sorry, unique tokens. Numbers is the next part. So it's the process where we take the whole text data and we divide it into tokens. Tokens are effectively the smallest individual elements of a text. It could be words, it could be characters. And here you can see the example, what we have done. We've taken the text and we have divided them into tokens. Every individual word is like a token. So these are the 6 tokens that we see in the text. And there can be different ways of tokenizing, but here we are just doing the word tokenizer. Now we have to somehow figure out a way to take these tokens and give it to the ML models. And this is the machine learning model could be any of the things that we have talked about thus far. We can look at a supervised learning model like a logistic, decision tree, random forest, gradient boosting, or we can look at an unsupervised learning model like a k-means clustering. We can use any of the different approaches that we have discussed so far. So we can take that text data in a tokenized form and we have to feed it to the ML model. But remember, we have to somehow convert it to numbers. Machine learning can only work with numbers. The maths can only work with numbers. It cannot work inherently with categories or text. The first part is tokenization, where we break it into chunks, where we break it into individual words. And the second part is what we refer to as vectorization, which is the process of converting each token into a number. And how do we do that? How do we take each and every text and convert this into a numeric form? This process is what we call vectorization. And there are many, many ways of doing that. So we'll start off with a very basic approach, an approach that has been widely used in the field of natural language processing for decades. We will start with a very basic approach, a very naive approach. And from there, we look at more and more advanced approaches. And then when we study neural networks, we will discuss approaches using deep learning. But in all of these approaches, this idea still remains the same. Okay, so in the field of NLP, all the approaches that we see, the core idea still remains the same, where the first step is you are tokenizing the data, you're breaking it into individual chunks, you're breaking the entire text data into individual chunks. That is what we refer to as tokenization. That is the first part. And the second part is after you do tokenization, you are trying to vectorize the data. You're trying to vectorize the data and you're trying to convert that data into individual, into numbers. Now let's understand how are we doing that? How are we actually doing the vectorization? So one of the very first things here is to build what we call a vocabulary. What is a vocabulary? Vocabulary is referred to as the unique words in the entire data set. So you have, let's say, a lot of text with you, and you go through all the sentences, you go through all the tokens across all the sentences, and you find out what are the list of unique words. Okay, so what do I mean by this? Let's take an example. Let's say we have data set one, which is he is a good boy, she is also good. So imagine we are working with a review case study, e-commerce reviews. So you buy a product in Amazon and you give a review. And second is you buy, another person buys a product in Amazon and he or she gives a review. I'm just giving an example. So let's say review one is, and document can be anything. We are looking at one more very new terminology right now called a document. What is a document? A document is simply one row or one observation. So in the field of natural language processing, one document stands for one row or one observation. That is what one document stands for. So here, one document can be one review. You write a review in the e-commerce platform, so that is one document. One document can be one review. One document can be one Facebook post. One document can be one Twitter tweet. So this is what each and every document can be, right? A document can be a review. It can be a Facebook post. It can be a Twitter tweet. A document can be an article. One document can be one article. One document can be one news story. So one document corresponds to one news story. That is how we define a document. One document is a so one document corresponds to uh, one article. So this is how we define a document. A document is an observation. So you go through the two documents right now and you find out what are the list of unique words across both the documents. Or in other words, what are the list of unique tokens? Because remember, I told you, as per the basic approach we are following, one token is one word. It can be different also, but here we are saying that one token is one word. So you go through all the documents in your data set and you find out that, hey, what other list of unique tokens do we have? And that is what we call a vocabulary. Okay, so you build a vocabulary. You first find out a vocabulary. And in a real world scenario, imagine you're working with real Amazon reviews data and you're going through tens of thousands and hundreds of thousands of customers who have written reviews across different products that they have purchased. And if you go through all those hundreds and thousands of reviews, and if you find out what are the list of unique words, the vocabulary will easily run into several tens of thousands of words, right? Because if you try to find out the list of unique words that people have used across their reviews, then you will find lots of unique words. So that is what we call the vocabulary. Now, what we will do is we will these are the broad approaches that we have. We have multiple approaches. Bag of words is the broad approach that we will use. There are many ways we can do this. And what is bag of words? Bag of words is a very simple feature extraction technique. This is the simplest one, where we try to understand text in the form of word counts. So we try to understand this text in the form of word counts. So we will find out the unique set of words, which is the vocabulary, and then we will find out how many times does a particular word appear in a particular document. We will simply look at the word counts. So we will represent each document by measuring the presence or absence of vocabulary words. And as you can see, this completely ignores the grammar or structure in your data. The corresponding grammar or the structure in your data is completely ignored. We will not take into account the underlying grammar or the underlying structure in our data. We will completely ignore the underlying grammar or the underlying structure in our data. So that's the way how this process is working out. That's the way how this overall process is working out behind the scenes. So the grammar or the structure will be completely ignored. How is it happening? Let's see that. So we have, once again, back to the same example. We have document 1 and document 2. And we have the two documents right now. And first thing that we do is we find out what is the list of unique words. So we create the vocabulary. Let me remove the index part. Index is just an internal way of representing the, the mappings. This is not needed for understanding. Let me remove that for a minute. And what you do after that, first you create the vocabulary, which is the list of unique words. And after that, what we do is we go and we find out that, hey, you list out every single unique word or unique token along the columns. You list out every document along the rows, and you're simply doing word counts. You're simply looking at the word counts. You're finding out how many times each and every word or each and every token is appearing in each and every individual document. It's a simple word count based model that you created. So if you see the first row, the document 1, if you see the word good has come 2 times because the word good has appeared 2 times here. See the second one, like if you see the word is has come 2 times because it has appeared 2 times here. And very interesting, the word person has appeared 0 times because the person is not there in document 1. So you're simply measuring each and every document. You're simply representing each and every document in terms of whether certain words are present and whether certain words are absent. It's a very basic feature engineering technique, which is completely ignoring the context of the data. Just the presence or absence of vocabulary words is considered. But the real meaning of the sentence, what do the words really mean? What does the sentence really mean? The context is completely hidden. But these kinds of models were extremely popular for a long time until we had more powerful approaches, which we'll see later. But remember, this approach completely ignores the context. It completely, ignores the meaning of the word. The context is ignored. If you look at document 2, Radhika is coming 1 time. So the word Radhika is present once. Is come 1 time. And the word person has come 1 time. Okay, and the word good has come 1 time. Because the word good here is present once, rest are 0. And this is what we call a document term matrix or a DTM, where you're representing every single document in each row. Each row consists of a document, and each column consists of a unique term. So each and every row we have a document. There's a document in each and every row, right? So every row we have a document, and in the column you have each and every unique term. And this is what we call a DTN or a document term matrix. Now, there are a lot of challenges with this approach. Let us talk a little bit about what are the challenges. One of the biggest challenges is, if you see, one of the biggest challenges would be with respect to the vocabulary. So if you have 100, 1000 odd documents, and if you try to find out the list of unique tokens, if you try to find out what are the list of unique words that we have across all the documents. So across all the documents, what are the list of unique words that we have? If you try to find that out, then you will see that the vocabulary size will be very large, and also you will end up having a lot of redundant words, right? A lot of redundant words which really mean nothing. And also, let's say if I do some spelling mistake, I'm just giving an example. He is a good boy, and let's say let's say I'm using a short form. Let's say for some reason I'm using a short form and I'm using GD. Instead of good, you're saying GD. I'm just giving an example, right? So we are not using the word good. But let's say instead we are using the word GD. Okay, I'm just going to show you. Let's say we are using the word GD. Now, if I do that, if I use the word GD instead, what will happen? What will happen if I use the word GD instead? So now when we look at the vocabulary, there'll be one more unique token called GD. Now I remember this token means nothing. The GD actually means nothing. It's just an abbreviation. But just because we found another unique word, because Python found there's another unique word that we have, it will not look at the meaning, right? But it will see, hey, I think there's something unique that I see called GD. So it will still create a vocabulary token for that. And when you create the DTM, you will still end up seeing a unique word like GD in the vocabulary. And this is present one time, this is present 0 time. Look at this, because GD is present once here, but GD is not present here. This is the kind of representation you will get, but obviously GD means nothing. These are some of the challenges that you will start to see. So as you can imagine, when you are working with real text data, there is a lot of data cleaning and data pre-processing that you will have to do. So before you even start working with your data, you will have to really put a lot of effort to clean and pre-process your data. You will have to put a lot of effort to clean your data and to pre-process your data. You will have to clean and pre-process your data. So take the original text data. So you will take the original text data and you will have to clean and pre-process your data. That's the way how you will have to work it out. So that's the way how you will have to work it out. So take the data and clean and pre-process your data. That's the idea. That's the core idea how we will work with it. Now, and what is the meaning of cleaning? What is the meaning of text cleaning here? There are a couple of ways we can do that. And all of this we are doing to improve the quality of our document term matrix. Why are we talking about text cleaning? Because we want to improve the quality of our DTM. We want to improve the quality of our DTM. We want to make sure that whatever document term matrix we are getting is of high quality. So a lot of text pre-processing we will typically do. And what are some examples of text pre-processing? Well, if I have to give you an example, imagine we are working with e-commerce review data. Hey, people write all sorts of reviews, right? You go to a restaurant, you eat something, and you love the food. Let's say you love the food, you love the restaurant, you love the ambience, and you write a review which is somewhat like, "Hey, I love the food," and you share your email ID, you share your contact number, and you say, "Okay, please contact me at john so and so at email.com, gmail.com," and you will write a long review with your contact information, other things, and all that. Now, if you think about it from a real world scenario, you have shared some personal information, right? Yes, you have talked about the restaurant, you have talked about the food, which is great. All that will be part of the document matrix, DTM, the tokens. But your personal information doesn't matter, right? Let's say at the end you say my mobile number is 97499777777, whatever. So that mobile number, that 97499777777, even that will be part of my this thing. Even this will be a term in your document matrix. That's the problem. You don't want this kind of thing to happen. You might have used some special characters like star, right? You might have used some special characters like star, star. People do that all the time. They write dot, dot, dots, right? So some dot, 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 dot they will do. Now, the problem is when the DTM is getting created, all these kinds of erroneous characters, all these kinds of so-called redundant tokens will find their way into the document matrix. So even before you do, and even before you create your DTM, you will have to take a lot of care to remove these redundant tokens or to remove these redundant characters. That is one kind of data pre-processing we will have to do. The second thing that you will have to do is you will have to make sure that you remove the stop words. You remove the stop words. What are stop words? Stop words are effectively uh, stop words are effectively high frequency words which are present in most of the documents. They are what we refer to as stop words. So stop words are high frequency words which are present in most of the documents. So for example, we are looking at words like is and the and which really do not add any meaning to the document, right? Imagine we are trying to do sentiment analysis. I'm just trying to take a very ballpark example of sentiment analysis here. Let's say let's say we are trying to do sentiment analysis. Think about it. When we do sentiment analysis, Words like ease mean nothing, right? What is ease? Ease means nothing. So in real world sentiment analysis, when we are trying to perform, words like ease and the, for, they don't mean anything, right? Because these kinds of words will be there for negative reviews also. They will be there for positive reviews also. So when we do sentiment analysis for negative reviews also, the words like is and the will be there. And for positive reviews also, the words is and the will be there. So that's the way how we will have to work it out. Okay, so when you do real world sentiment analysis, we will have the words like is present for negative reviews also. And when we do real world sentiment analysis, we will have the word is that will be present for positive reviews also. That's the way how we work it out in practice. So we will have to remove these kinds of stop words. We will have to remove these kinds of high frequency words. We can remove them. Another kind of data pre-processing that we do is we do lemmatization. What is lemmatization? Lemmatization means, let's say, oftentimes, you will have different verb forms of the word, right? Action verbs. So the base word is like, which is what we call the lemma, but there are different ways the word will often be used, right? You'll have liking, likes, liked, likely. So it all refers to the same base term. They're all referring to the same base term, right? But you are using the word in different ways. That's the idea. So they're all referring to the same base term, but you are using the word in different ways. That is what we are talking about. That is what we are talking about here. So how you do that is you can convert all of them into the same base word called like, because otherwise what will happen, you will end up getting individual columns for these words. So for liking, you will have a separate column. You'll have separate tokens, right? They'll be treated as separate tokens, but it's not needed, right? Because they're all referring to the same base word. Because remember, I told you that this model, the approach that we are following right now, we are not focused too much on the we are not focused too much on the meaning of the word. The context of the word is not really taken into account. We are only focused on the presence or absence of certain words. So we just need to take all the similar words which are part of the same lemma and convert it back to the same lemma. This is what we do as part of lemmatization. And one of the good things about this would be that we have a cleaner DTM, we have a cleaner document term matrix. And that document term matrix is nothing but a featureization technique, right? We're just taking the text, and it's a way of doing feature engineering on text data, isn't it? So at its core, that's what we are doing. At its core, all that we are doing is we are doing feature engineering. We are performing feature engineering on text data. That is what we are doing at its core, right? So we have some text data, and we are performing feature engineering on text data. So we have some text data, and we are performing feature engineering on text data. That's the idea. We are performing feature engineering on text data. That's the core idea. That's the way how we are working it out. We are performing feature engineering on text data. So now the other kinds of things we can do is we also have something similarly called stemming. Stemming and lemmatization are very similar. Only thing is in lemmatization, the lemma is usually something that is present in dictionary. It is a meaningful word. But in stemming, there are different algorithms that are used for that. This is the kind of stuff that you will find in English Oxford Dictionary kind of thing. Like, so you look at a word meaning, and oftentimes the stem words, the base words, the lemmas will be listed out, right? And there are algorithms for it, how it's done. And if you see that if these are the original words, the word stem is lick, okay? And and usually the stem is not or may not be present in the dictionary. There are different algorithms, and there are different rule-based algorithms that can be used for doing that. And this is the kind of stuff that will find its way into the dictionary. If you look up any word in the dictionary, you will typically find these word stems will also be listed out. So the idea would be to go and make sure that we take the data, we clean the data, and we all set. Okay. Uh, this is a small slide I put up here where, what happens when you work with web data. Web is a very big source of text data. It's not part of the discussion here, but just wanted to mention the term that you use different Python libraries like Beautiful Soup. BS4 is a very, very popular library that you can work with. Okay, and you can scrape data from the web. Okay, so we can have data in different formats, right? I can give you some data in a CSV file. I can give you some data in a text file, whatever. But you can also scrape your data from the internet. Okay, so you can scrape your data. You have got typical HTML, right? HTML tags are there, table tags are there, body tag is there, paragraph tags are there, and you can scrape your text data. And you can pretty much do the same kind of pre-processing techniques that we are discussing. But I want to clarify one thing. I want to clarify one thing and reiterate this once again, that there are limitations to this bag of words technique. We are only taking into account the presence or absence of vocabulary words. We are just looking at the counts, how many times different types of words are present. We are only looking at the presence or absence of vocabulary words. We are just looking at the count. We are only looking at the count of how many times word one is present and how many times word two is present. We are just looking at the presence or absence of vocabulary words here. We are looking at the count of how many times this is present or how many times that is present. Just the count is what we are focusing on generally. Just the count is what we are focusing on generally. And if you see, if you look at it, if you look at these two sentences, I had washed my house and I had my house washed. Very interesting. See, these are the exact same words. You know why? Why is that the case? Because if you look at document one and if you look at document two, if you try to focus on both these documents, and if you try to follow the same approach that we listed out all this while, so find out the list of unique words. First, go through both these documents and find out what are the list of unique words. If you try to find out the list of unique words, you will observe that across these two documents, you have total 5 unique words. And if you want to create the DTM will look somewhat like this. Let me write it down for a minute. So that's your D1. I'm just going to write down the DTM for a minute. That's D1. That's D2. And these are the documents. And we have the unique words, which is I. So you will typically sort it in ascending order. So maybe you can look at the order of the word. So H had will come before. So first you will have the word had. Then you will have the word house. Then you will have the word I. Then you will have the word my. And then you will have the word washed. See what we are getting at? See how we have managed to find out the list of unique words. Okay, and now in both these documents, each of these words are coming one time each. Right? So the moment you convert these documents into a vectorized form, the moment you convert these documents into a numeric form, because that's the whole focus, right? Because we don't understand text. Machines don't understand text. We are trying to convert it to a numerical vector form. The moment you do that, the vectors look exactly the same. That's the problem. Because it doesn't capture the meaning, right? It's only looking at counts. So you can have two documents which have the exact same count of words, exact same number of words, but they mean completely different things. The meanings are completely different. And this is the limitation of this bag of words technique. This is the primary limitation that we will face with the bag of words technique. And obviously, despite this limitation, this approach is a very naive approach which performs really well for basic tasks. If you want to do sentiment analysis and other kinds of basic tasks like topic categorization, it performs really well. Because when you do sentiment analysis, you're looking at different terms, right? You go to a restaurant, you have some food. So oftentimes these approaches will work reasonably well. Because if a user is constantly using some negative words, then that will be highlighted. Okay, so the bag of words technique, although it is very simplistic, will surprisingly perform very well. And oftentimes it will be part of my base model. Whenever we solve real use cases, this will be usually part of my base model. So as part of the base model, we will do something like this. So now let us see how this will be applied in practice. We'll see a small example of an application, how to apply this technique in practice. Let us see that in action. And there are a lot of different types of pre-processing, as I said. Like first part is you remove the stop words, you do all of that, and there's another something else called part of speech tagging. So part of speech tagging is the process where you again take the initial text data and you try to find out what are the different part of speech in that text data. That is what we refer to as part of speech tagging or pause tagging. So like we look at a particular text and we find out the different words in the text and we try to find out what part of speech they correspond to. So I look at the different words that are present in the text and we try to find out what part of speech each of the individual words correspond to. Is it a verb? Is it a noun? Is it an adverb? Is it an adjective? So each and every word that we have, what POS they correspond, what part of speech they correspond to. So every single unique word that we see, uh, we can do some pre-processing this way. And we can use a machine learning model for doing that. We don't have to manually do it. There are different ways we can do this, but we can use some pre-trained libraries for doing this part. And I'll show you a beautiful library called Spacey in a while from now. And we'll see how inside Spacey, the Spacey package, there are so many different inbuilt methods which will automatically do this for you. So you can just take the text data as it is, and you can pass it through Spacey. You can pass it through a pre-trained machine learning model that's already trained. You already have a ready-made model that is available. You can pass it through that ready-made model. Behind the scenes, it is doing classification. It is looking at each and every token or each and every word in your text, and it's trying to find out what part of speech it corresponds to. Is it a proper noun? Is it a verb? Is it a determinant? Is it a noun? Is it a proper noun? And so and so. And similarly, we can also do something called named entity recognition or NER. NER is a short form that we use. So the core idea of NER is you look at the text data and you try to find out what are the different categories of the text? What are the different categories of the words that are present in my text? That is broadly what we do as part of NER. So when we look at named entity recognition or NER, this is broadly what we do as part of NER. We go through the entire text data and we try to find out what are the different categories of the words that we have in the text. So we have, let's say, the word or the phrase Barack Obama, and that is actually a person. So again, behind the scenes, it's a pre-trained model. It's already a ready-made model that is available that is looking at each and every collection of words, that's looking at each and every collection of phrases, and is trying to group those words into different categories. So we can say, okay, Barack Obama is a person. United States is a GPE, which is the geopolitical entity. 2009 to 17 is the date, and United States is the GPE, and this is ordinal. And there are different categories. You can Google out and see NERs. Again, there's a Spacey package which will automatically do NER for me. There are other ways of doing it. You can build your custom NER models. But behind the scenes, what we are doing is we are just doing classification. You give me some text data, and I'm trying to look at each and every word or each and every phrase in the text and trying to classify what is this, what is this, what is this. And all of these are related to feature engineering. We are simply taking that completely unstructured and dirty text data, the completely unpreprocessed text, and we are trying to find some meaning out of it. We're trying to find some meaning out of it, either by representing that in the form of word counts, by finding out how many times certain words are coming, or finding out what are the parts of speeches, or what are the named entities. So this is the core of what we are trying to achieve in terms of NLP, the fundamental approaches at least. Now, to put this in practice, what I will do is actually the hands-on is very easy. And this is just to give you a flavor of how it is done. There are different ways how it can be done. So first, I'll show you the Yelp hands-on. And then I will also show you the Spacey case study. I've got a file called Using Spacey, where I've given you some of the Spacey examples. So this is a beautiful use case of sentiment analysis that I will show you. So the objective now is I'll show you one case study, and then based on that, I will ask you to solve an exercise. That's the general pattern that we have followed. We did one exercise and ask you to solve an exercise so that we get some good practice. So Yelp is like a website where people can book different types of home services. So Yelp is where people can book different types of home services. You can basically book a plumber, you can book a carpenter, you can book. Okay, so that is what Yelp actually is. So okay, so Yelp is like a, a site where you can book different types of home services. Okay, so you can go to a restaurant, you can book a plumber, you can book a carpenter, and you can, after you complete the service, you can give a review, you can give a rating, and then you know that's the whole idea of the data set. So my data set looks somewhat like this. This is the real data set that we are seeing. Yelp.com, you can go to and check. Okay, this is the real data set. Every row corresponds to a review, and we have the different features of the review. Again, when you're running the code, remember, don't use G Drive, because G Drive is where I'm trying to take my data from Google. Yeah, I've already told you how to do this. You can download that file. You can download the CSV file, which I've already shared, and you can upload it separately on Colab. If you want to connect through Google, you can do that also, but you need to make sure that your file is there in the Google Drive location. Now, every row corresponds to a review. We have the business, whom you have reviewed, the date when you have reviewed, how much stars you have given. This is like a feedback, 1 to 5 star. Okay, so 1 star, 2 star, 3 star, 4 star, 5 star. So the rating is the stars that you've given. Text is what you wrote in the review, what you actually wrote. What is it that you wrote? How did you like the food? How did you like the restaurant? And user ID is the user who wrote the review. This is the unique identity column, right? So our focus is we will look at the text and we will predict the stars. This is what we are trying to do. You can ignore all the other columns. This is not important. This is not important. So the big picture understanding. So the big picture understanding that we have here is we are looking at the text, which is X. And based on that, we are trying to predict the stars, which is Y. That is the objective of this particular exercise. Okay, we are looking at the text, which is X. So based on the X, we are trying to predict the Y. Okay, so based on the X, we are trying to predict the Y. That is the problem that we are solving. So based on the input X, the text X, the input, we are trying to predict what is the stars, which is the Y. So you have the historical data, you have lots of reviews that customers have already given. You study that. That is part of the supervised learning approach that we are following. You study the already labeled data that customers have already given, right? This is the reviews that customers have already given. So you please study that labeled data that's already available, right? So you please study that. So whatever data we have, let's study that. Let's study the already available label data that we already have here. And on the basis of that, label data, let's understand the patterns. Let's understand what are the patterns that are typically playing out. Study the pattern, build a machine learning model, and on the basis of that, next time we have a new review. Next time we have a new review, we will try to predict what the stars will be. So this is the typical sentiment analysis use case that we have. From the existing data, you study the patterns, you try to draw the association, input-output combination, you draw the association that whenever the text is like this, the user is positive, and whenever the text is like this, user is negative. So you try to draw that kind of an association, and next time you go to some site and the user writes something, or you go to Facebook. Facebook doesn't have a rating system, right? So you take the data from somewhere where there is a rating system. Somebody will write the review and they will also rate you. So they will explicitly tell you how they are feeling. Are they feeling positive? Are they feeling negative? So they'll explicitly give a rating. So you take the data from that kind of a site and you build a machine learning model. And next time you can look at a platform where users are just writing text, right? Or let's say in the chat here, some of you are typing something. And let's say I'm asking you for feedback and you type something on chat. So you're not giving a rating, but you're just typing something. So I can use that model that I built and I can predict your sentiment. So next time I have a new text, I can predict what the sentiment is. Or let's say in Twitter, some user, some politician writes some post. Okay, so the sentiment analysis model will be used to determine the kind of comments that people are making, and based on that, how are people feeling? Okay, how are people feeling? There are a lot of geopolitical events that happened in the course of the last 1 month. And let's say some local leader posts something about, some country or whatever, right? Not naming any country, but then a lot of people would have commented, And based on that, the local leaders will get an understanding, hey, how is my vote base feeling? Because you're a leader in a constituency, right? And you have to keep your people happy. So you put out a post, you put out a tweet, you put out a Twitter tweet or a Facebook post, and based on that, hundreds of people comment, and each of those comments, and nobody is rating it, right? But based on the comment, the model will predict what is the sentiment. Are people positive? Are people negative? Did people like what you say? Did people not like what you say? Okay, so and these are very, very good, time-tested strategies that a lot of political parties are using today as we speak. Okay, election campaigns and all, what to say. In a big campaign rally that happens, there's a tremendous amount of NLP that happens. A lot of natural language processing is happening. A lot of sentiment analysis is happening to identify what kind of words to use, what kind of topics to speak on, what do people like. Okay, when you go to a constituency, when you go to a city and you talk about something, you should talk on something that people like to hear, that people are positive about. When the prime minister goes to some place before the campaign, now obviously the elections are over, but a lot of back end groundwork would have happened. It is not that they will go and create a random script and start talking about it. You will not go to a village and talk about US policy, foreign policy. Like nobody will understand foreign policy there. They are concerned about basic things. So you should know what people like. And before the script is prepared, a lot of these time tested strategies will be followed, where somebody will put out a post. Somebody, lot of the local leaders will put out posts. They will try to collect user feedback. They will try to collect feedback from their voters. Okay, how are you feeling about this? How are you feeling about this? And this is pure play sentiment analysis that will happen. And then they will collate all that information, and then the final script will be prepared for the leader of the party. Okay, and there are companies doing this work actually. There's a lot of companies which are doing this work. Okay, and if you look at an example, okay, so this is I'm just trying to give an example in the Indian context. Okay, this is this is in the Indian context. Okay, but you can also look at you know it's in the other context as well. This is a company called IPAC, which is very, very instrumental in the state elections in our country, in India, right? So uh, IPAC came to prominence. This is a company founded by a person named Prashant Kishore. You might have heard of it. Very, very popular figure in political circles and also media. He used to come in a lot of debates before. Now I think that he has his own party, so it's calmed down a little. But uh, it came to prominence in 2014 when they were instrumental behind the uh, massive mandate that BJP won. Okay, and we had our prime minister. Okay, so and after that, in all the state elections, after that, ever since. So if you see IPAC uh, perform phenomenally in all the state elections. So they have state units where they set up different, they set up the state units, and in each of the elections they campaign, and they use a lot of data science actually. A lot of data science they use, and this is you can actually see, very interesting the kind of work they do. Okay, and I feel the best way to learn about a company is to learn about their work, right? So if you look at data analytics technology, you can see what kind of work they do. Okay, I think they have not explicitly listed out, but you get the idea. You get the idea at a very high level, the kind of work that is involved. There's a lot of research analytics work. There's a lot of work that is available on if you see our work. So okay, I think not this one. So if you take a look at it, there's a lot of work that uh, they'll be doing on analytics. A lot of NLP related work will be there, right? So all of these kinds of roles will be available. Okay, yeah. Now moving on, we have the X, we have the Y, and what I'm doing again is a principle I've already talked about. We are trying to only consider two categories because the ratings and the stars, there are total 5 different categories of stars, right? If you see how many different categories of stars do we have? We have 5 different categories of stars, right? We have 1 star, 2 star, 3 star, 4 star, 5 star. So broadly speaking, we have 5 different categories of stars, right? Broadly speaking, we have 5 different categories of stars. So we don't need all the 5 different star categories, right? We do not need it. We don't need to identify between a rating 1 and rating 2 because both are bad, right? We don't need to identify between, or we don't need to explicit. Please separate between rating 4 and rating 5 because both are good, right? So rating 4 is also good, rating 5 is also good. So no need to segregate between 4 and 5. Both are good. So the objective here is to group all the different stars into two broad categories, either good or bad. Is it positive? Is it negative? So we would have done some pre-processing here, and we are saying, hey, if the stars are 1, 2, or 3, if it is 1 or 2 or 3, we will call it bad. If it is 4 or 5, we will call it good. So we are taking all the different star values, unique star values, and we are grouping it into two broad categories. If it is 1 or 2 or 3, we will call it bad. If it is 4 or 5, we will call it good. 1 or 2 or 3 bad, 4 or 5 good. So we have two different classes, binary classification. And why are we doing that? Remember, I told you that this will ensure that you are able to build a good quality model, a more accurate model. Okay, so you will be able to generally build a more accurate model if you do it this way. So the model will be more accurate, because otherwise what will happen is there might be a lot of these kinds of errors or false positive errors that you might get. You might have a lot of cases where model predicted 4-star but actually 5-star. We don't want those kinds of mistakes to happen. We don't want a scenario where model predicted 1-star but actually it's 2-star. See, both are bad, right? You actually did the prediction right, but just because you're having more number of classes, you need to be exact. You need to be absolutely accurate in your analysis, but that is not needed. The exact accuracy is not needed. Anyways, so now we move on. Let's see the process. We do tokenization. So we use something called count vectorizer to perform the tokenization. This is the step-by-step approach we are following, and count vectorizer is again part of sklearn feature selection, feature extraction. You can see all of these are part of sklearn. Sklearn is the machine learning library in Python, so we are using count vectorizer. There are other ways to do it, TF-IDF. There are multiple ways to do it. I'm focusing on the fundamental ones to give an idea to all of you. So the stop words equal to English, we will ignore all the English stop words, and lowercase equal to true. That means if we have two different words, let's say you've got the word CAT in uppercase and the word CAT in lowercase, what it will do is it will convert everything to lowercase. Because there is no point in having the same word coming in two different cases, right? Otherwise, in the DTM, two separate instances of the word will be created. That's not needed, right? We do not need to create two separate instances of the word. So what it will do is it will go and it will convert everything to lowercase. It will convert everything to lowercase, and it will effectively, create a DTM by converting everything to lowercase. That is the core idea. That is what it will do behind the scenes. It will convert everything to lowercase. Okay, vect.fit and get feature names. You can find out the list of unique features, and there are 25,496 unique features we are having, or 25,496 unique words we are having. This is the real data set. Okay, we have taken a real data set from Yelp, anonymized, obviously. It's we have taken some open source data, and when we go through all the reviews that people have posted, when we go through the entire data set of all the reviews, we can see there are total 25,496 unique terms. Okay, these are the kind of features that people have used. You can see already start to see that so much of data cleaning is required, because when people write real reviews, they're writing all sorts of stuff, and as I told you, lots of special characters, dot dot dot, lots of numbers. Some people would have shared mobile number, some people would have shared address. Like somebody would have said, hey, I hated the food, it was horrible, food was very bad, here goes my mobile number, 77799, please have your manager John call me, I'm very frustrated, I live in this place. All that is not important, right? Where you live, what is your mobile number, what's your birthday. You say, hey, I know I came for my birthday, my birthday was 20th January, and I hated the food. Okay, hating the food is one thing, you can mention something about that, but you say my birthday is 20th January, that has nothing to do with the sentiment, right? So, but when the DTM will be created, your birthday 20th Jan will somehow be a column. So all that is useless. You can already start to see that out of those 25,496 features, many of the features are useless. Many of the words are redundant actually. Like Z, 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 Z. Somebody would have written Z 5 times. You will see all these kinds of things happen. Anyways, this is how the DTM will look like in practice. So when you use count vectorizer, you will end up getting something like this. Okay, you will have all your documents or all your reviews along the rows, and you will have the unique words along the columns. Okay, you will have all your documents or all your reviews along the rows, and you will have all the unique words that will be listed along the column. So that is how the DTM broadly will look like. Okay, Now we can complete this in a pipeline. What we can do is we can use a pipeline, and in a pipeline we can use count vectorizer and multinomial Naive-Bayes. Remember, Naive-Bayes is a classification algorithm. It doesn't have to be Naive-Bayes. You can use any classification algorithm. Python will not complain. The code will still work. But generally for text data, we prefer using a Naive-Bayes algorithm. Naive-Bayes is something that works usually well for text data. But ultimately, you will still try and test it out. Okay. So first thing, you go and use count vectorizer. You take the text and you try to convert it into a document term matrix. You convert it to a DTM. Okay. You ignore the stop words. You remove the stop words. You convert it to lowercase and you create the DTM. And the second step that you do is you build a multinomial Naive-Bayes. So that's the way how we work it out. It's a very, very basic, text processing pipeline that we have created. You can see. So the biggest learning from this entire thing, you can see this code is exactly the same as what we discussed. There's nothing different. Although we are discussing NLP and text data, you can see that there is nothing different in the rest of the code. The only new learning, the primary learning that we had over the last 1 hour is how do we take text and how do we represent that text in a vectorized form? Because once we are able to represent our data in a DTM matrix format, now the algorithms will take over. The same approaches will work: training data, testing data, build a model, train accuracy, test accuracy, classification report, confusion matrix, precision recall. All those things will remain exactly the same. Because remember, machines will only look at your data in the form of an array. That's all that machines care about. They will look at the array and that's all they care about, right? That's the way to look at it. Machines will look at the array and that is all that they care about. And once you have your data in that array form, that's it. That's it. That's all that is needed, actually. That's all that machines care about. Machines will look at your data in the array format. And once you have your data in the array format or the DTM or the document term matrix format, once you have your data in that form, now you can absolutely go and you can pretty much use any of your existing classification models. You can use any of your existing regression models, your clustering algorithms, any of those kinds of things you can use going forward. So that's one way to look at it overall. Okay. So you can ignore the rest of the part. Deep learning part we will discuss later. Obviously, we'll come to that conversation. But I hope everyone's clear until here. Everyone's okay. So we are having a pretty decent model. You can see, and you can also see there are two classes, good and bad, and you can see. And obviously, very very obvious that the number of negatives are less, right? So obviously, if you look at my actual data, the support value, support stands for the frequency. That means in my test data, how many number of negative reviews do we have and how many number of positive reviews do we have? And very clearly we can see that the number of negative reviews is comparatively, the number of negative reviews is low. So the number of negative reviews is very low, which is expected. The company is a good company. People are happy with the services. So people will not say bad things about the company, right? So the number of negative reviews are on an average low. So there are lesser examples of negative reviews, but there are more examples of positive reviews. That's the inference we are getting, right? So there are lesser examples of negative reviews. There are more examples of positive reviews. So the model that you finally end up building tends to be better in identifying positive reviews. So the positive review scores are higher. You can see there's 95% F1 score, which kind of means that, okay, whatever sentiment analysis model that we have built is better at identifying positive reviews, but it is not that good in identifying negative reviews, which is understandable because one is there is less number of examples, and second is if you look at the negative reviews, it's harder. Negative reviews are harder to detect. There can be sarcasm, there can be a lot of different ways people can write a review, and negative reviews can be substantially harder to detect. So that's one of the ways to look at it. Okay, there are a lot of examples of these kinds of comments that we can look at. A couple of these examples I wanted to share with you. So this was a post. This was something that happened quite some time back. It's not a new thing, but I'm sure some of you would have heard of it already. So this was a post by a person, right? You can see, and I know the text is not perfect, but you can make it out, right? So thank you for sending my baggage to Hyderabad and flying me to Calcutta at the same time. Brilliant service. Die Indigo. This was long back. This is 2017. And if you see, the model responded saying, glad to hear that. So most likely it was a rule-based model. It looked at some of the keywords like brilliant and service, but it did not really understand the context of the word, right? So you can already understand that although it's a negative review, but identifying negative reviews can be very hard. There is sarcasm, there is inherent sarcasm, which the model is unable to catch. So a simple word count based model, a simple count vectorizer model that we talked about all this while, will not be able to solve these kinds of problems. Most likely Indigo was using a count vectorizer model and they were not able to understand the inherent meaning of the sentence. They were just looking at the word brilliant, and the word brilliant came, so okay, glad to hear that. But I mean, so obviously that is not what the person meant. Right. So these are all very real, use cases that I wanted everybody to understand that sarcasm is something that is very hard to, very hard to detect in a real world scenario. Or it can be a more neutral comment. There can be a more neutral comment, right? So I mean, so you can have a more neutral comment as well. Like this is the one that happened some days back. And if you take a look at this, very interesting. So this person actually paid for a window seat. So this person paid for a window seat, and as is the current trend today, everybody wants, everybody will post things on social media, right, for their own set of fame. So here this person goes and says, "I paid for a window seat. Where is the window?" Right. So you can see this is not like a negative comment. This is not like a negative comment, but in the context of the business, this is still negative. So this person actually paid for a window seat, but when they went and when he sat beside those, there's no window. So the window seems to be closed. So I mean, you will see the Indigo plane sometimes like the row is a window row, but you don't have a window. It's like there's this complete an obstacle there. So that's it. So this is the neutral comment, right? If you look at either of the techniques we discussed, like uh, the count vectorizer approach, there's no negative words a person used, right? Where is the window? So it's not saying good, bad, nothing. There's no feedback the person is sharing. So the count vectorizer model will completely miss it. Okay, the word count based model will completely miss these kinds of instances. Okay, but if you really look at the context, the sarcasm is being sarcastic, right? This is a very sarcastic comment. So it's actually a negative feedback because you paid for something, you didn't get it, right? A horrible service, actually. You didn't use those words, but you get the idea why negative reviews are very hard to detect. Okay, so that's about the basic ideas of NLP. We'll obviously extend the conversation and see this in more detail. We'll see exactly the other things that are involved in this. But I hope everybody is understanding the foundational ideas of what NLP is. And as I said, like now that you get this basic idea, you can connect the dots and you can solve any kind of exercise with this, right? So next time you get any kind of text data, like for example, I've got this another beautiful case study on regression test case analysis. Okay, so now whenever you get a text data, you can figure out that, hey, let me represent my text data in a vectorized form. So how can I represent my text data in a vectorized form? So you can try to do that. Okay, so you can see this is a very similar case study where you're doing regression testing. Okay, and as part of this, what we are trying to do, this is my data set. You can see we've got different test cases, we've got different test case descriptions and all that. And based on that, we are trying to decide whether we should select the test case or not. Okay, so it's a test case selection that we are trying to do. So based on the different attributes of the test case, we are trying to figure out whether we should select the test case or not select the test case. So this is the output Y, and all of this is part of my input X. You can take the description column, and all that we are trying to do in this document term matrix or DTM based approaches, we are trying to represent all this as part of my features, right? So all this is basically part of my input X, and you're trying to represent this whole thing as a document term matrix or a DTM. A DTM is how you're trying to represent this whole thing. Okay, so another very similar example will be this one. So another very common kind of data will be support requests or support tickets. So let me download this data set to show you in a better way. So we have got a slightly bigger data set. You can see this is actually a service request data set from New York City. And you can look at any kind of support ticket. Let's say customers are raising support tickets in your organization. And typically in the support ticket, what will they have? They will have a description column. Okay, that is also a very good use case that you can do NLP with. You can convert that description into a kind of a document or matrix, a DTM. Okay, and on the basis of that, you can try to categorize. You can categorize requests into different buckets. You can say, okay, you know what, we have a we have a request like this, we have a request like this, and you can try to you can all of a sudden try to categorize your request into different buckets, okay, into different categories. You can say, okay, request 1 is corresponding to hardware and request 2 is corresponding to software. So depending on the issue description, your users are raising different issues, right? So depending on the issue description, what you can do is you can try to identify what is the category of the issue and which team it should be assigned to. Okay, so you can use that, or maybe another simple example could be, like a topic categorization, like some of the things that Google News is doing. I'm not saying Google is using this basic technique. They're not. Obviously, they're not. They're using neural nets and other things to do that. But at a very broad level, you can look at the entire news story as X. The whole news story. The news story consists of, let's say, 1,000 words. It's the 1,000 word news article that we have. So the entire news story is like the X, and the news category is like the Y, and we are trying to do the prediction. So we are trying to do the prediction on the basis of that. So based on the news story that we have, which is X, we are trying to predict the category, which is Y. Another similar use case I'm trying to highlight here, you can see, very interesting. So people have raised, users and citizens have raised different complaints. And often it is a good practice to combine concatenate different columns. You can see there's a separate column called complaint type, and there's a column called complaint description. So you can actually go and concatenate the two. You can create a single text column. That's a part of pre-processing we can do. And then we can do a document term matrix, a DTM. Now, what is the business use case of this problem? What can we do? How can we use this data set? Well, very interesting. You have something called created date. You have something called closed date. So what you can do, you can create a new column. You can actually insert a new column and you can say, what is the difference? Okay, so we can calculate a difference. Okay, this is part of my available data. This is something we are doing based on whatever data is available, not something we are doing for new data, which is we already have some data where this is given. So we have created date, we have closed date, and now we will calculate a difference. Okay, so what is the difference between the created date and the closed date? And that will tell me how much time it takes to resolve the issue. Okay, so that will tell me how much time it takes to resolve the issue. So right from the time the issue was created till the time the issue was closed, how much time did it take to resolve the issue? So this is what you can find out. So let's say this is 56. I'm just taking a ballpark number. This is 70, right? Whatever, I think we need to convert it to numeric type. So this is 56, this is 70, right? This is 92, okay, 80, 82, this is 1. So very interesting. What you have here is you're able to understand how much time these issues have taken to resolve in terms of minutes, whatever, right? So you have supervised learning. You have input X, which is the complaint type and the complaint description. Users have raised tickets. Users have mentioned what the issue is about. And you also have an output column, which is the output Y, the difference actually. Let me just highlight that in red. And what you are trying to do is you are trying to uh, use this input X and trying to predict the output Y. So you study the patterns. You study the patterns between the keywords in the description and the amount of time it takes to resolve the ticket. Right. This is the data pre-processing and the problem framing that I talked about. You create the output column. Another very interesting learning in this exercise is you are actually creating the output column, isn't it? Like many of the past exercises we did, we already had the CSV file given. We had the outputs given to us. We know what is X, we know what is Y. We are simply modeling. But in a lot of real world problems like this one, this is a very simplistic exercise, but you can see in this exercise, the output is actually not given. So when you look at your initial data source, there is no output. There's no target column that you initially have. So you have to study your data and you need to use your common sense and your understanding of the problem, and you need to find out what is the target. You need to oftentimes create your target. So you create the target difference column. And now you try to study the patterns. Okay, features like this is the patterns you're trying to study, X, Y combinations. Okay, so you convert this to a DTM. You take the X and you convert this to a document term matrix. Every single row is a description and every single column is a unique word, and you're looking at word counts. Okay, so that's the way how we go about it. And next time we have a new user. So this is how you build the model. And next time we have a new user who raises a ticket. Okay, if you have a new X, a new ticket is raised, the model will predict what is the corresponding Y. So next time there is a new ticket, we will predict what is the predicted Y, how much time it will take to resolve the ticket, which could be very powerful, right? If you're able to predict in advance how much time it will take to resolve a ticket, it could be a very, very good use case in customer support, right? So customers, when they raise an issue, they will know in advance how much time it will take to complete or resolve the issue. It could happen through chat support, it can happen through email support, or it could happen through a more formal ticketing engine like ServiceNow. Okay. So this was to give you a very broad understanding of the different things that we have. How do we go about it? And now we will do a small exercise based on what we have discussed, and we'll take it forward from there. All right. So once again, let's start with the conversation. Let's start with the solution of this SMS text classification exercise. And although we are discussing this in the context of an SMS data set, this can be anything. It can be an email data also. It doesn't necessarily have to be SMS data. You can also do this in the context of email data. And all the spam classification algorithms that we see, even in the context of emails, they are also operating the same way, right? So next time when you get a new email, the models are trying to predict whether that email is a spam or a ham. Okay, so you have a lot of labeled data. You have lots of emails that are already labeled. You're showing the machine lots and lots of existing emails. Emails like this are spams. Emails like this are hams. You're training the model on a lot of labeled data in terms of how emails look like. And next time there is a new email, we are trying to predict, is that a spam or is that a ham? So that's the way how we are looking at this exercise. Very similar to how we did the Yelp classification problem. And we will do this using a simple count vectorizer approach. And from there, we look at word vectors and all that, right? So that's the agenda. So first we load our data. And as rightly mentioned, the data is in a different format. So the headers are not there. And this is the way, this is a TSV file. TSV file stands for tab separated value file. If you go to the SMS folder and if you just double click on the file, you will see it's a tab separated value. It's a tab actually. Okay. And this is the way you can load it. There are other ways you can also load this data, but you have to explicitly say headers equal to none. And you have to also explicitly state the name of your columns, label and message. And once we do that, you will follow the exact same approach to see how we take the data. We do the train test split, right? We do the count vectorizer, right? Tokenization, vectorization, and the process is exactly the same as what we covered. So this is how the overall document term matrix will look like. We have got all the messages, which are the documents along the rows, and we have the unique terms along the columns. Unique terms are basically the key. And then we are simply using a multinomial naive-based model. You can use any classification model here, but here we are using naive-based to build the classification model. And we can find out the confusion matrix and we can evaluate how well this model is doing. I think compared to the Yelp dataset, I think this is doing far better. We are getting 97% test accuracy. But we discussed about other best practices. We should do cross-validation and we should look at the confusion matrix to evaluate it at a more detailed level, how it's really doing. Okay. And if you relate to it in the spam classification, what is very important is to identify false positives. FP is very costly. So when we had this conversation on confusion matrix, we discussed that ideally both the errors are bad. False positive is also bad, false negative is also bad. But here false positive is more deadly because false positive means model predicted your email is a spam, but in reality it is not. That means when you get a message, the mail has been classified as a spam. So the mail goes to the spam folder, but in reality, it is not a spam. And that is a very dangerous situation, right? So model predicted your email is a spam, but in reality, your email is actually not a spam. So that is a very dangerous situation, and we have to do whatever it takes to reduce the number of false positives. Okay, so this is the general solution that we have here. Rest of it is using deep learning, which we will discuss later on. So once I talk about Keras and TensorFlow in a short while from now, we will understand the deep learning based solution. Okay. Now, all these approaches that we discussed, in all these approaches, we are looking at word counts. And we discussed that if you only consider the word counts and if you only try to represent documents in terms of word counts, they will not completely represent all the characteristics of your documents. So the meaning of the documents will not be properly represented. We talked about that. And that is exactly where we look at another technique of vectorizing the data, which is using word vectors. This is the other way how we can represent our text data using something called word vectors, where the meaning of the words are taken into account. Okay. At a very high level, uh, imagine we have this kind of an equation that we are trying to solve, right? So we are trying to solve a mathematical equation using words, right? It's an incredible, right? So king plus man equal to queen plus what? If I ask you this question, I mean, the human brain will be able to draw relationships and draw associations, and we are inherently doing that by default, right? When you are asked this question, you are also inherently drawing word associations. You're looking at gender, you're looking at, okay, king is to man, so queen is to what is the most similar thing. So your human brain is also trying to, do something very similar. And what we want to do is we want the machine to also do something exactly the same. We want it to understand what the words really mean and draw relationships between them. In other words, the end result, the end objective of what we are trying to achieve is this. We will take each and every word and we will try to use some technique to represent each of these words in a numerical vector. And that is exactly what we refer to as word-to-vec. Word-to-vec is an approach where we take each and every individual word, we represent each and every individual word as a vector form. We try to represent each and every individual word in a numerical vector format. So we have the word king, we represent the word king as 440. We have the word man, which is 480. We have the word queen, which is 410. And we have the word woman, which is 510. You're trying to solve a mathematical equation. So when you're asked this kind of thing, so it is quite literally you're saying, hey, 440 plus 480 equal to 410 plus what? So you're trying to like solve the equation, algebraic equation. So you try to find the number and then you try to match that number with the corresponding word. This is the way we will solve it. And moment you're able to do that, all of a sudden, a whole host of interesting applications, becomes possible. So you can all of a sudden find similarities between words, which otherwise we could not have done. If we were just using the count vectorizer or the document term matrix based approach, just looking at word counts, we could not have done these kinds of things. Now all of a sudden, I have these four words with me: plane, bed, dog, and boy. And all of a sudden, what I can do is I can find out which are the words which are very similar to cat. You know why? Because we can represent the word cat as a vector of numbers. So the word cat is a vector of numbers. It will be a vector of 5 numbers, 10 numbers, whatever, howsoever many numbers you want to represent. So we can represent the word cat as a vector of numbers. We can also represent the word. Um, we can also represent the word plane, bed, dog, and boy as numbers. So we can represent this entire data in a vector of in a numeric form. We can represent this whole data in a numeric form, and now we can use distance formula. We can now use distance formula to find out which of the words are similar. Which of the words are similar? So we can use distance-based algorithm to find out the most similar words. Okay, so all these applications start becoming possible based on word2vec. So this is what word2vec is. You're converting the words to a vector form. So what does word2vec do? What are the other kinds of things it can help me solve? It can help find gender relationships based on distance formula because these are vectors, right? King is a vector, man is a vector, woman is a vector. It's a sequence of numbers. So all you're trying to do is you can now all of a sudden try to find the distance between man and woman. You can find the distance between king and queen. You can find the distance between swim and swimming. You can find the distance between country and capital. So all these distances you can actually try to find out now. You have two words, you can try to find out what is the distance between those two words using things like Euclidean distance. This is the magical technique now. And the same way that you can represent words as numbers, you can extend this idea into something called document vectors or doc2vec. You can try to now represent entire documents as numbers. Now remember, friends, we already did that. It's not something we haven't done it. We already did that in the last discussion. The problem is in the last discussion, we used simple word counts, right? There also we had two documents. We had he is a good boy, she is also good, Radhika is a good person. We had those documents, but that time we were only representing the documents in a vectorized form using word counts. That is the problem. We will try to do something very similar now. The same way that we can represent words in a vector form, we can extend the conversation. We can represent entire documents in a vector form. But this time, those numbers will represent the meaning of the document. The inherent meaning of the documents will be represented. So at a very high level, how does Word2Vec work? I will not get into the details of it because, as I said, each of these individual topics are much topics, massive topics. The underlying theory is very deep. It's not the objective. It's not the objective of the training to sit and show you a bunch of theory, but at a very high level so that you have an intuition what it is, and then we'll go to practical applications, right? So at a very high level, what is Word2Vec? What exactly is going on behind the scenes? Right? How are we doing this? How are we actually achieving this? So before I come to that discussion, let's look at one more. Let's look at one more intuitive understanding of Word2Vec. This is another one of my snippets where I try to explain this approach. So this is what we are doing in Word2Vec. This is the end result, right? Then I'll show you how it works. So this is the end result of what is going on inside Word2Vec. So you have got four words right now: lion, tiger, cat, and plane. And what we are trying to do is we are representing each and every word in the form of its word embeddings. So we are converting lion into a vector of numbers, cat into a vector of numbers, tiger into a vector of numbers, and plane into a vector of numbers. So we have each and every individual word, and we are trying to represent each and every individual word as a vector of numbers. So the word lion is a vector of two numbers, f1, f2. The word tiger is a vector of two numbers, f1, f2. The word cat is a vector of two numbers, f1, f2. And the word plane is a vector of two numbers, f1, f2. So we have each and every individual word, and we are trying to represent each and every individual word as a vector of two numbers each. Okay, so we are trying to represent each and every individual word as a vector of two numbers each. Why two? It's a hyperparameter. You can decide how many numbers you want, but I took two here because so that it is easy to visualize. So lion is 0.11, 0.12. Now these features mean nothing. What is f1 and f2? You might ask me, but f1 and f2 are actually hidden features of a neural network, which we will discuss when we come to our discussion on neural nets later on. So we are yet to talk about that. So once we start discussing about neural nets, we will get a better understanding what hidden neurons and hidden layers actually are. But at a very high level, remember that this f1 f2 stands for hidden features. So what is this f1 f2? They are nothing but hidden features. So they don't have any inherent meaning. So we don't know what these features mean. So f1 f2 just stands for hidden features. Okay. So lion is a vector of these two numbers. Tiger is a vector of two numbers. Cat is a vector of two numbers, and plane is a vector of two numbers. And now we can look at the right hand side, and we can represent the each and every individual word as a vector of two numbers each. X-axis we have f1, y-axis we have f2. So x-axis we have f1, y-axis we have f2. We are simply representing the data in the right way, and we can plot each and every individual words now. So you can plot the word cat somewhere here. So what is the word cat? The word cat is 0.09.11. Can you see, all of you? Look at the word lion. The word lion will be 0.11, 0.12. This is 0.11 here, 0.12 here. So you're able to represent every word in the two-dimensional coordinate plane. And all of a sudden, we are able to understand and form groups and clusters of words. How powerful is this? See, clustering is again fundamentally based on distance. We talked a lot of clustering in our yesterday's discussion. So you can relate to this a lot better. So once you are able to represent your words in a numerical way, and these numbers are again coming based on deep learning. These numbers per se don't have any meaning, but the numbers as a whole. So f1, f2 individually doesn't have any meaning. Okay, just accept it for a minute. It doesn't have any meaning. It doesn't mean anything. But as a whole, 0.11 and 0.12 is telling you something about lion. So as a whole, 0.10 and 0.11 is telling you something about tiger. So as a whole, these two numbers are telling you something about plane. So when you go and plot it out in this coordinate axis, when you plot out the words, you can start to find groups and clusters of similar words. You can use distance formula to say that, okay, you know what, lion, cat, and tiger seem to be very similar based on their word vectors, but plane seems to be something very different. So you can all of a sudden find synonyms and antonyms which are otherwise not possible. And as I said, you can decide how many vectors you want to represent with each and every individual word. And the same way that we can use word vectors, we can represent words in a vector form, we can extend this conversation and instead work with document vectors. So the same way we have word vectors, we can now extend the conversation of word vectors and documents. If you look at entire sentences, entire documents, documents are collections of words, right? If you look at a document, if you look at a sentence or a document is a collection of many words. So now you can take that entire document and you can represent that entire document as a vector of numbers. So a document is a collection of words. One document is, let's say, consisting of 20 words. So now you can look at each and every individual document. You can look at each and every individual document and you can represent each and every individual document as a vector of 20 words or as a vector of 5 words. You can do an average. So let's say if I have a document, Radhika is a good person. There are 5 words in the document, right? We talked about that use case in the last discussion. If I give you a document, Radhika is a good person. So Radhika is, let's say, 2 numbers. Is 2 numbers. Is 2 numbers. So let's say each and every word you can represent as 2 numbers. So the entire document as a whole, if you look at Radhika as a good person, the whole document, the whole sentence as a whole will be nothing but an average of the word vectors. So the whole sentence as a whole, the sentence as a whole will be an average of the word vectors. Radhika 2 numbers, is 2 numbers, 2 numbers, good 2 numbers, person 2 numbers. So you take an average of these two numbers and you get the the average document vector. So that's the way how we think of document embeddings. And as I told you, like it doesn't have to be two. You can also represent every word as a vector of 300 numbers. And we'll look at some beautiful animations in a minute from now. And moment you do that, the more the number of numbers you're using, the richer the context. The richer the context. If you're using 300 numbers, 500 numbers, so if you're representing every word as a vector of 100 numbers, you're having more context. And more the context, the better the representation of the word. But obviously, we cannot visualize 300 dimensions in a coordinate axis. So what we can do is we can do something called PCA. So we discussed about principal component analysis in the towards the last part of yesterday. End of yesterday, we discussed a little bit of basic PCA based on some questions. So what we can do in PCA at a high level is we can take these 300 dimensions at a very high level. You don't have to know PCA to know that, okay? We talked about it yesterday, but we can now take these 300 numbers and we can represent these 300 numbers using only 2 dimensions. So we don't need 300 dimensions anymore to represent lion. So we can compress the information that is present in all these 300 dimensions into only 2 principal components. So principal components are nothing but 2 new features that we are creating. So now lion is 0.07, 0.09, tiger is this, and now we can create 2 coordinate axes for the PCA coordinate axis, PC1, PC2, and we can plot the same thing here. So the idea is the same. The only thing is that we are now taking a very high dimensional data. We are representing a very high dimensional data in terms of only 2 or 3 dimensions. We are able to reduce the number of dimensions, which is why PCA is often referred to as a dimensionality reduction technique. We are able to represent the data in lesser number of dimensions, yet retaining the most important information. So the information is still retained. So you can see very clearly that even when I do PCA, even when I represent this 300 dimensional data in terms of 2 principal components, I am still able to see that lion, cat, and tiger are very similar, and plane is something very different. So this is the core idea of what word embedding and word to vec actually is. Okay, so the very first word to vec model came up from Google. This was back in 2013, right? So before that era, we were using a lot of traditional approaches like the ones I talked about in the last discussion. So Google was one of the pioneers of this specific algorithm called the skipgram architecture, which they used behind the scenes to generate word vectors. And what they did in 2013, which is actually very recent, 2013 is almost a decade, right? It's just a decade, almost a decade, just slightly more than a decade. That's it. So it's not been a long time since this technique came out. And if you see, what did Google actually do? So Google used the Google News dataset. So when they did this, they actually used part of the Google News dataset, which is about 100 billion words. And the model that they built, the word vector model that Google created, it consisted of 300 dimensional vectors for 3 million words and phrases. Okay, I think now we can understand this a lot better, exactly what I explained all this while. So based on the training that Google did, it trained the model on the entire Google News dataset, on part of the Google News dataset, and and every word or phrase is a vector of 300 numbers. And if you want to use that, you can actually use the Google News dataset here as well. There are a lot of other kinds of word vectors that are available. Like for example, there is something called GLOVE. This is from Stanford University. So GLOVE stands for Global Vectors for Word Representation. And here also you can see that the GLOVE vectors are available for different datasets. We have it available for Wikipedia. We have it available for Common Crawl, for Twitter. So for different datasets, these word vectors are available. And this is actually a very interesting point because you might be wondering, why do we need different word vectors or different word-to-vec models for different datasets? Why do we need that? Because the vectors that are learned, the word vectors that you're creating, they depend on the training data that is used for training those word vectors in the first place, right? So if you're looking at the Wikipedia dataset, the model was trained on the Wikipedia data. Think of it that way. The model was originally trained on the Wikipedia data. And on the basis of that, in that context, those word vectors were learned. So at the end of the process, you will have each and every word, and you will be able to represent each and every word as a vector of 300 numbers or however many numbers. If you see the different variants like 50D, 100D, 100D means 100 dimensions, 200 dimensions, 300 dimensions. There are 300 dimensional vectors also. 4 files are present. All the files are present if you download the glove.zip file. Okay. So what it means is the model has been trained on the entire Wikipedia 2014 data, that is data until 2014. And we have managed to create 300 dimensional vectors for all the unique words. And how many tokens we have? We have got 6 billion tokens. So across the entire Wikipedia dataset for until 2014, we have 6 billion tokens. 6 billion is a huge number, by the way. Tokens could be either words or phrases or individual characters in certain cases, right? It's a 400,000 vocabulary. It's a massive vocabulary size. And for each of those unique words, we have managed to generate 300 dimensional numbers. Remember, somehow we try to understand what is the meaning of the word in the context of Wikipedia. Now that part is very important. In the context of my data set, not something in a generic way, because different words can mean very different things in different data sets, right? Like I'll give an example to you. If you look at the word network, the word network means very different in the context of a telecommunications networking company, like Cisco. If you look at, even if you go to telecommunications companies like Airtel, Vodafone, the word network will mean very different. But if you look at the same word network in a general context, I'm talking about everyday communication, general day-to-day communication. Or maybe you go to Facebook and you use the word network. The word network means something very different. Network might refer to a social network. Or if you go to LinkedIn and in general communications, in job searches, if you're using the word network, you will not talk about telecommunication network there, right? So you will talk about job network, networking and all those kinds of related professional terms that we use. And if you go to some other domain, maybe if you're going to some technical literature, you're going to a conference and you want to present a IEEE paper, right? You want to present a paper on deep learning neural networks. So there, if you use the word network means something very different. So what I'm getting at here, friends, is that the same word can have multiple meanings in different contexts. So that is why the context is very important. How this data has been trained, what kind of data set was originally used to train the data is very, very important. Now, that is a very technical topic, which is not the scope of the conversation right now, but the idea is important. And if you go Google and if you search, you will find different types of data sets like Common Crawl, Twitter. In Twitter, the words can mean very different, right? If you look at it, what it means is we have trained the entire word-to-vec model on the Twitter data. That means the words mean very different things in the Twitter context. If you try to train a word-to-vec model on your organization data, the context will be very different because the way people use certain words in your company are very different from how people use those words generally. So generally in everyday day-to-day WhatsApp communication, people will use different types of words. But when you're interacting in an email, when you're interacting in support tickets, you will not use the same words in the same way. So understanding the meaning, understanding the context is very, very important with respect to the data. Now, at a very high level, just for 2 to 3 minutes, let's understand how it works. Okay, this is the technical part. The slides mention everything. If any people are interested, that's what I've tried to do. I've tried to strike a good balance so that I'm not skipping the thing. You have all the content with you. If you want to read, there is everything available for you in the slides. You can go over it, but at the same time, I want to at least do justice and tell you what is it. Expectation is not to get into it, but so that you at least relate to what is it, because it's a very interesting technique, so that you understand and relate to how it is learned, what kind of architectures are used, how it is happening behind the scenes. Very, very high level. I want to give you the idea. So what we are doing in Word2Vec is we are trying to somehow understand the context words. We are trying to find out this concept of a nearby word. So we are looking at each and every word. You look at a particular document or you look at a particular corpus. We call it a corpus. So in the case of Wikipedia, you will look at the entire Wikipedia corpus and try to find out how are different words getting used. So for example, let's understand what is considered near. How do we define the meaning of near? So if you look at the word in, you are trying to find out what is to the left of in and what is to the right of in. So to the left of in, we have the word rises. There's a small typo. It will be rises. Actually, we can think of it as rise if we consider lemmatization. So if you do lemmatization, rises and rise mean the same thing. Anyways, that's a different conversation. So if you focus on the word in, with respect to the word in, to the left of it, we have rises. To the right of it, we have the. If you consider a window size equal to 1, and these are important terms, when I show you the hands-on demo for how to create a Word2Vec model, you will set these parameters. These are hyperparameters. So you can use something called a window size to determine the context. You can say window size equal to 1, and you can use a particular window size to determine the context. That's the idea. So we can use window size equal to 1 to see which word is to the left of in and which word is to the right of in. So that is the context of using the window size. If we take a window size of 2, again with respect to the word in, you can see to the left of in there are two words, sun and rises. So in rises, in sun. To the right of in there are two words, the and east. In the, in east. What are we trying to achieve through this? What are we trying to achieve through this? See how we are actually trying to understand how a word is getting used. So we are looking at the corpus, the training corpus, like either a Wikipedia or a Twitter or a Google News, right? The original Word2Vec model was trained on the Google News dataset. So we are looking at the corpus, the training corpus, right? The internet scale data, like, is very similar. Like even the current large language models, like a GPT model or a Gemini model, all these LLMs are also trained in a similar way. I'm not saying the exact same way, but the idea is very similar. So they will also have a certain amount of training corpus, a certain amount of training data, and we are also trying to constantly train the models on that entire training corpus of data. So that's the key idea, right? So you look at each and every individual word and you try to find out how the word is getting used along with other words in the corpus. So in this corpus, if you look at the word in, how is the word in getting used? And that's how the relationships are getting learned. So all this while I've been talking about word relationships, right? King to man, queen to woman, right? I was talking about the word network. You can see, I said the word network means different things in different contexts. So if your training corpus is, something like a telecommunications company, let's say you're trying to build a support chatbot in Reliance Jio. So if you're trying to build a support chatbot in Geo, and if you look at the word network, so there's a lot of technical literature Reliance Jio or Airtel will have. So maybe all their network engineers will have some kind of support manual. You call up a call center and you ask about, hey, my internet network is not. So the word network will mean something very different. So whenever the term network is getting used, it will somehow learn the association of the word network in that context. But if you use the word network in a different data set, it will mean something very different. So this is the core idea of Word2Vec. Now, how is it done? That's the technical part, which I will not get into at this point in time. But once we cover neural networks, you will eventually understand this. At a very high level, we use something called a skipgram architecture. Okay, the name of the architecture is actually use skipgram. And at a very high level, what we are trying to do is we are looking at a neural network. We will look to build a neural network. We don't have to do it. There's a library that will do everything for you. Okay, but this is a behind the scenes implementation. We use a skipgram architecture, which means it involves a neural network. You will give a particular word as input, and it will predict the context words as output. That is what the skipgram architecture will do behind the scenes. This is the high level idea. Now let us understand exactly how it is done. What is the implementation? Let us see the implementation of word to vec, because that is far more important than all this theory. So let us actually build a word to vec model from scratch. So we'll do two ways. One, we will look at a word to vec model from scratch, and second is we will use a pre-trained word to vec model. So I have a folder called word to vec where I've shared both the demos. So demo number 1 is where I am building a word to vec model from scratch, and demo number 2 is where I'm using a pre-trained word to vec model. That means an available model like a Google word to vec model, a GLOV model, like that. So let's look at the very first demo. Let's look at the very first demo and let's see how to build the word to vec model from scratch. And I feel this will be more realistic for you guys, because if you're trying to do something in your organization, if you're trying to do something in the field of your work, you have some data with you, you have some text data with you have some document data with you. So you cannot use a Wikipedia model, right? Because the Wikipedia word to vec model was trained on that kind of data. The Wikipedia model was trained on that specific type of data, right? If you look at the Twitter model was trained on that specific type of data. So you cannot just go and build a word to vec model on that kind of data. That is not relevant, right? So you cannot just go and build a word to vec model specifically on that kind of data. That doesn't make sense. So what you will need to do is you need to take your own data, you need to take your own TXT file or CSV file. You will take your own data and you want to build your word to vec model specifically to your own data, specific to the kind of data that you have. That's the whole idea. That's the way how we will do the entire word to vec. Now, moving on, if you see that we are loading the data here, so I'm going to quickly go over it. So we have already given you some a CSV file here, unlabeled data. And this is unlabeled. Why? Because we only have the reviews. We don't have any targets actually. So I have a simple CSV file which looks somewhat like this, or it could just be a text file. It doesn't have to be a CSV file. It can be a simple text file, a notepad file, or a Word document, whatever. It doesn't have to be in a particular format. You just need text. We are doing a simple cleaning function, cleaning the data using some regular expressions, right? And this is a bit of data cleaning we are doing to remove any special characters, any spaces. You can see some quotes are there. Some of these. This is some amount of web scraping we would have done. So some of these HTML tags like BR, self-closing tags, all this is getting included. So all this we will try to remove. And this is the clean data. Next, what we do, we go and convert the review to a word list. So we get a list of words. And then this is the final code to build the model. Okay, this is the most important part. Okay, this is the main code that we are using to build the model. Okay, so we are using a specific library in Python called gensim. You will have to install this package, pip install gensim we will do, and it has a ready-made function for word to vec. Okay, so what you do, you simply give your documents as an input. Documents is your data, the thing that we created. So we already have some text data, we cleaned it, and that's my document list that we have right now. So we give it as an input argument. And what are the other parameters? We have min count equal to 5. This is very important because this specifies ignore all the words with total frequency less than 5. Why is it important? Because remember, the whole idea of word to vec is based on context. So you want to only include words which are at least present a certain minimum number of times. So min count equal to 5 is important because you want to only consider words which are present minimum for 5 times. That's the idea, right? If a word is not even appearing in the document, think of it this way. If a word is not even appearing in the document, then it doesn't help. If a word is not even present, then how will it help? It will not even help, right? So the word needs to be ultimately present in the document for you to learn the embeddings and for you to do the analysis, right? If the word is not even present, then you cannot even learn the relationships. Relationships can be learned only if the word is present. If the word is not even present, how will you learn the relationship? You cannot learn any relationship, right? If the word is not even present. Think of it that way. That's the context. That's the context we are getting at. Okay. Vector size equal to 50. Vector size equal to 50 stands for the embedding size. This is the embedding size which tells me how many numbers we are using to represent each and every word. So this is also like a hyperparameter. You can specify how many how many numbers we want to use to represent each and every individual word. So we are just using 50. You can set any number you want. Number of CPU cores. Window size is equal to 5. We talked about that. And again, window size is the hyperparameter. You can specify that. If you want richer context, if you want to understand the meaning of the word, looking at, so 5 basically means 5 to the left, 5 to the right. So that means you're looking at a overall context of 10. That means there is 5 on the left, 5 on the right. So the bigger the value of window, the richer the context. But you have to also ensure that you don't take a very high window size, because if you take window size 100, it means nothing, right? 100 means you're looking at 100 words before to understand what that word means. That is not like, if you look at typical English sentences, let's say if I say Ram is a good boy. So Ram is a good boy consists of only 5 words, right? So when I look at the word boy, so boy is Ram. So I can draw association up to a point. But if I go 100 words back, I cannot draw association, right? It doesn't make any sense. So typically window size will obviously be less than 100, less than 50. It will be a smaller number, somewhere in the vicinity of 10, 20, maximum up to that, not beyond that. Okay. And again, it's a hyperparameter. You have to try different values and see which one works the best, and epochs equal to 10. So once you do that, the end result, I'm not training this in the class. It will take time. It will take time to train. But once you run the code, you will end up getting something like this. So you will end up getting the word embeddings is specifically for the words, individual words. So you can see we get the word embeddings for great. So the word great is now a vector of 50 numbers. Okay. You can see the word amazing is a vector of 50 numbers. This is the end result of the word to vec. And if I try to show you the similar words, you can see. So if I say what is the most similar to amazing, you can see these are the words which are most similar to amazing: incredible, awesome, outstanding, so on and so forth. Okay, this is actually building a word to vec model from scratch. And as per your use case, whatever document I've shared, you can literally take the same file. You can use your own text data, just put it here, and you can create word vectors on your own data in a matter of minutes. The second example that I shared with you is very similar, but this is using a pre-trained model. In this case, we are using a pre-trained model like the like the GLOV model, like the uh, Google Word to Vec model, something like that. We are actually using. So here I'm specifically loading the GLOV model. Okay, that's pre-trained. It's already trained on the Wikipedia data. Remember, so I'm just using that model, and the end result you can see. Okay, prince, man, princess. You can again see each of the words are vectors of 50 numbers. Why 50 numbers? Because we are using the 50D one. There are different variants. Remember, I told you there are 50D, 100D, 200D, 300D. So we're using the 50-dimensional one. Already, it's a trained word-to-vec model, so we can see the numeric representations of each and every word. And remember, just to reiterate, I mentioned this before as well. So these numbers do not mean anything. If you look at these numbers right now, these numbers mean nothing. So you have got each and every word, which is a vector of 50 numbers, 100 numbers. So these numbers mean nothing. So per se, the numbers do not tell you anything. You're not able to understand anything from these numbers per se. Okay, but you will get some very, very interesting relationships. For example, if I ask what is the most similar to Ronaldo, remember glove was on the Wikipedia data, so it understands general terms that people use. So what are the words similar to Ronaldo? And it will tell me the words similar to Ronaldo are Ronaldinho, Kaká, Figo, Messi, Rivaldo, and so on and so forth. So we are able to understand similar words based on the context. Okay, and this was the question that we started our discussion with. Woman to king is man to queen. You can see that we are able to get the most similar words. So woman to king is man to queen based on distance formula. And we can also get some other very interesting things like, look at this one. Sachin to Saurav is Tendulkar to Ganguly. It even does a very nice job of finding relationships between popular names. The name has to be popular. That if you look at Sachin and Saurav, they would have come in Wikipedia many times. A lot of people would have cited, the opening batsman, India, like cricketers and all that, right? So it's able to understand the relationship between the words. It doesn't know their names, right? I mean, so in this case, the word to vec model doesn't understand what is a name, what is a planet, what is an object, what is a car, what is cricket. It doesn't know anything. It is just looking at how the words are coming, how the words are getting used, and it is just forming associations. And it's a very powerful approach, very powerful approach. You can see Sachin to Javagal is Tendulkar to Srinath. And finally, even country capitals are done nicely. Riyadh to India is Saudi is to Delhi. So Riyadh is the capital of Saudi, whereas India is the, Delhi is the capital of India. You can see that. Okay. And as I told you, you can now extend the conversation and you can find sentence vectors from word vectors. This is the core idea. So until now, we discussed about how we can represent each and every individual word as a vector of numbers. We can take every word and we can represent a word as 50 numbers, 100 numbers, and now we can extend the conversation and we can instead create document vectors. So now we have a document, let's say we have laws of physics. So each of the individual words we can represent in a vector form. We have the word laws, which is 50 numbers. We have the word physics, which is 50 numbers. So we can take each and every individual word and we can effectively form a vector of words, a vector for the sentence as a whole. So that is what we refer to as sentence vector. So very basic way we can do it is averaging. There are different ways we can achieve it, but you can see the most basic way how we are achieving this is averaging. So see the code here, all of you. So title one is laws of physics. So we are getting the word to vec for laws. We are getting the word to vec for off. We're getting the word to vec for physics. Okay, and one very important thing, off and is not a stop word. Remember, moment we talk about word to vec models, word embeddings, there is no concept of stop words. Stop words were only until the last approach that we discussed, count vectorizer. But the moment you talk about context sensitive models, stop words do not make any sense. Like stop words are equally important. So, when you talk to a chat GPT, the kind of stop words that you're using, the prepositions, conjunctions, determinants, what is your name? So all these words are important. So is, of, the, so all these are also important words. So whenever you're working with word embedding based models, remember you should never ignore stop words. You should always consider stop words. So anyways, I've got the individual word vectors for these words now, laws of physics, and all I'm doing is I'm simply saying W1 plus W2 plus W3 by 3. It's a very naive technique, but it surprisingly works very well. You have different approaches we can use for it, but this is the most naive approach that I wanted to show you, how you can generate a document vector. And this is a much better way of representing or vectorizing the document instead of using word counts. Okay, because now all of a sudden we are able to somehow represent the document in terms of its average meaning. Average meaning. So we are able to somehow represent the meaning of the document, what the document actually means. So now with this in mind, let's get a move on. This pretty much wraps up the basic NLP part that I wanted to cover with everybody. So the objective was to show you how to work with text data. So all until yesterday, we were working with tabular data, structured data, and this entire conversation is to bridge that gap, is to show you that, hey, if you have some kind of text data, this is the way you can work with it. Okay, so this is the fundamental discussion. So after we learn about neural nets in the next part of the session, we can relate these ideas even for text data. Okay, so neural networks will be a very generic topic, but once we discuss neural networks and deep learning at a very high level, we will be able to relate, and we'll be able to use neural networks even in the context of text data. So that is the thing that we will attempt to do. So now what I will do is, before we jump into neural networks, that is for the next phase of the discussion. But before we do that, let us take a small digression and talk a little bit about this Azure, because the Azure environment is something that everybody has set up at this point in time. So I want to take some time and talk about the Azure environment and how you can effectively do some basic machine learning on Azure. So whatever ideas that we have covered until now, except for deep learning, whatever we have seen, how can you use a machine learning studio? How can you create a Jupyter notebook? How can you build a simple machine learning model on Azure? What are the different things that are available in Azure at a very high level? Okay, we try to focus on this is not a session to teach you Azure. I wanted to reiterate, this is not an Azure training, but this is just to tell you, this help you relate that, hey, these are the ways you can use Azure. So we'll see all the components, but at a very high level, so that you know and you have a very good big picture understanding in terms of what is possible and what is not. Okay. So all of you, I would request you to log into Azure, you can use the same credentials that are given to you. So all of you can log into Azure. And once you do that, once you are in Azure, I'll start with the next part of the conversation. All right. So now that we are logged into the Azure portal, what we will do is all of you please search for Azure Machine Learning Studio, right? So you can just again follow on the steps right now, what I'm doing. So you can just type something called Azure Machine Learning. And so there are a lot of different services that you have in Azure. So if you just click on it, there are many, many services you will find. There are virtual machines, there are all the typical cloud storage services, and a ton of different things that you see inside Azure. We are not interested in all these things. We are only interested in the machine learning and the AI services of Azure. You can just type Azure Machine Learning. And once you click on machine learning, what we want to do is we want to create a machine learning service. So I already have a resource that is created here. And let me show you how you can also create a new resource. You need to go to this page. You need to click on create and click on create new workspace. So click on create new workspace, and you will automatically, your subscription will reflect here. Automatically, your subscription will reflect here. And you have to create a new resource group. So under the resource group section, you will see a drop down. So I already have some resource groups available. All your resources will be bucketed under the resource group. But for you, what you need to do, you need to create your own resource group. That is what you will have to do. You need to create your own resource group. So you can just click on create new, and you can just give it a sample name. And once you do that, once you give it a sample name, you can just give the name of the resource here. So I can just say some demo, some demo. So the date today is whatever, like 14 or 17, whatever. You can just give it some sample name, and automatically the rest of the things will get filled up. And once that is done, click on review and create, and click on next, 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 finish. Very straightforward process. This will take 2 to 3 minutes time to complete. That's why I'm not asking you to do it right now, because this will take time. So once it completes, once this process is done, what you will get is something like this. So the resource will be created. And after the resource is created, you can click on the a demo 11 April Azure Machine Learning resource. This is the resource that is created, the workspace that is created right now, which is grouped under the resource group called demo, present in the East US region. And now you can click on something called Launch Studio. This is the Azure Machine Learning Studio. It's a web app where you can build, train, test, and deploy machine learning models. Okay, you can do the entire thing end to end inside Azure Machine Learning Studio. So all the different aspects of the life cycle that we have covered until now, starting right from getting the data, getting the trained data, all of the different pieces that we talked about, all that entire thing we can do inside Azure Machine Learning Studio. So click on the Launch Studio button. And once you click on the Launch Studio button, a slightly different URL will open up, ml.azure.com. So this was Portal Azure. So now you'll see something called ML Azure. And here you will see the entire machine learning interface. Okay, so it looks really exhaustive. Uh, there's a whole bunch of options you will find. The model catalog lists out several different types of pre-trained machine learning models, and many of them will involve generative AI. So we're not worried about Gen AI right now. Obviously, that's not the scope of our discussion, but you can actually see that there are many pre-trained generative models that are also available. So you can see O3 model. O3 is one of OpenAI's latest CAT completion models. There is also the recent GPT 4.1 model. The DeepSeek version 3 is also available. Llama 4 is from Meta. These are all available. These are all the typical large language models that you can see. Okay, uh, which you can straight away use. You can also separately decide what kind of task you want to work on. So I think these are all language modeling tasks, which are again are not so relevant to our discussion that we had over the last few days. So our task is, let's say, something like an image classification. We will talk about image classification in the second half today and some part of tomorrow. So if I have an image classification task, then these kinds of models will be more relevant for me. Okay, so we can fine tune this based on the kind of tasks that we are trying to accomplish. Okay, and based on that we can use the models. Anyway, so authoring environment will give you the different types of the different options that we have for authoring. So this is the different types of options that we have for authoring. So we can create notebooks. We can build an automated machine learning model, and we can build a machine learning model using the designer interface, and prompt flow is something for Gen AI. We can ignore this one. So it's very nice. What we can do is we can actually create a Jupyter notebook on the cloud. So you can click on create new file, and you will get an option like this. You can give a file name, and this is how you can actually create a Jupyter notebook on the cloud. So I've got a working Jupyter notebook here, which I wanted to show you. So this is a Jupyter notebook that I have created on the cloud, and you can pretty much like do the same stuff. You can pretty much do the same stuff like import pandas, import numpy. So all the usual stuff that we discussed, pd.read CSV. So all the usual stuff we can continue doing here as well. It's just a normal Jupyter notebook that we have. Now, only difference is that remember Jupyter notebook is basically the application, but it needs some hardware to run on. So what we need to do is we need to set some compute. And in my case, I already have a compute which is active. So if you go to the compute section, I have a compute which I already created. In case you don't see this, in your case, you will not see the compute. And you don't have to do this. It's just to test you. Okay. You can click on new, and you can create a compute instance. And you can click on CPU, and you can basically select a very, very basic compute instance from here. Okay, so you can choose a basic one. You can choose a very basic compute instance from here. Okay, maybe $0.9 an hour, whatever. You can choose a very basic, compute instance from one of these options. So I will restart the compute instance. Let me start the compute instance just to show you the demo. It will take a moment to start. And once the compute instance is started, it takes a while to start. Okay, you can see. I can directly access Jupyter Notebook using that compute instance, and even VS Code Web. See how cool this is. So we were all we have got something called Visual Studio. Okay, so in our training we were all using Google Colab, right? Colab is the Jupyter application we were using, but another very, very popular application for doing and working with notebooks is VS Code. VS Code is also another very popular application, and you can access all these applications on the Azure cloud. Okay, so you can go back to notebooks. You can see that this kernel is right now starting. The compute is right now starting. And after this compute starts, I can basically run all these cells right within Azure. Okay, so you will not even, so you can upload a file, you can work with it the same way. Okay, so you get the idea how popular Jupyter Notebooks actually are. So it's not something that is only there for Colab. It is something that is a very generic standard. And once we connect to the VM at the backend, then we can go and connect to a kernel. Kernel will be a typical IPython kernel. I can show you. I can just wait for this to start, and then we'll connect to the IPython, the Jupyter kernel at the back, and then you can run these cells pretty much the same way. Okay, so that's the idea. So we'll wait for this compute to start. And while this starts, what I will do is I'll take you to another very interesting section called the designer. So the designer interface is where you can actually create pipelines from scratch. Okay, so this is what you can do in the designer interface. You can actually build a pipeline using a simple drag and drop mechanism. So you can go to this thing called designer, and you can click on classic, create a new pipeline using classic pre-built components. Okay, so you can go and create a pipeline using classic pre-built components. You can use pre-built components, and you can build a pipeline completely from scratch. Okay, so you can build a pipeline completely from scratch. So that is what we are trying to achieve in this designer interface. So click on plus. I'll create a new pipeline as a small demo. And once we come here, I'll go and drag and drop a sample data set. Let's say the sample data I want to take here is the adult census income data. So what we are trying to do here is something very similar to a case study that we covered yesterday. We are trying to look at the different features of a particular household, and we are trying to predict whether the household is rich or poor. If you want to see the sample data, you can right click and click on preview. Okay, or you can work on a different data set also. It doesn't have to be this. If you want to work on an iris data set, we can do that also. So I took some time to upload the iris demo here. So I already did that. And if you want to see the iris data, you can click on preview. And this is the same data set that we have worked on already, right? You can see the data profile, you can see the rows, the columns, and you can see a basic preview of your data. Takes a while to run. Okay, anyway, it's taking a little time, but you get the idea what the iris data is. I think we all know this already, right? So you can click on preview, and it will actually show you the data set, steeple length, steeple width, petal length, petal width, variety, and we want to use these 4 features to predict the variety. So that is what we want to do here overall, right? So then we come to the component, and in the component we we will go and use a train test split. So data transformation, we will use a kind of a split data. This is a split data that we will use, and what we will do here is we will split the data into training data and testing data. Okay, so on the training data, we will use some algorithm. So we will use in this case, this is a classification problem, right? This is a classification problem. So we will use something like a decision tree or uh, something very similar. We can use or maybe a multi-class logistic. See, this is what I was mentioning. The algorithms are a little different. Okay, so the sklearn algorithm names and the Azure algorithm names are a little different. So we call it fast forest, quantile regression, decision forest. Okay, you can see boosted decision tree. This is actually called gradient boosting. They don't call it gradient boost, they call it boosted decision tree. And this is called random forest actually. So there are different types of the terminologies are a little different. Okay, and there are some new some different algorithms you will also find specific to Azure. But the core ideas are very, very similar. The core ideas are exactly the same. Okay. So let me use a multi-class logistic regression. Let me use a multi-class logistic regression here. So this is the algorithm that I'm using. Let me auto zoom and what I want to do, I will do train model training. I will drag and drop train model, and this is the model.fit x train y train we are doing. Okay, can you see the data set? This is the split, right? The training data is here, and the algorithm is here. So we are actually doing logistic regression dot fit x train y train. Okay, and once that is done, you can double click on the train model. You can set the feature, the label, sorry, the label will be variety. The name of the output column is variety. Click on save, and that's it. Very simple drag and drop. So now the entire model training workflow is done. And now the last part is model scoring or model evaluation. So you can again search for the respective section here, model scoring, and you can score the model. So based on whatever model that we created, so now we will look to score the model. So we take the trained model, we take the trained logistic regression model, and now we take the test data. This is the test data that we take, and we try to get the predicted values. That is scoring, right? Scoring is what? Scoring means whatever model you have built. So now you will use that particular model and you will do model.predict. That is what we refer to as model prediction. So we'll use the trained model and we will use it for prediction. We will do something called model.predict. And after that, we will do something called evaluate model. So this is evaluate model. So you'll go and evaluate the model. So this is the whole pipeline that we have created. You can see the screen. This is the complete pipeline. You start from the original data, split the data, train test split, build the model, evaluate the model, and at the end of this process, we will see the confusion metrics. Okay, we'll see that. I'll run this pipeline for you. So this is the authoring that we have done. So let me, in the meantime, take you back to the notebooks for a minute. Okay, no, I think we want to continue. We want to continue. So let me run this. So configure and submit, and I will enter an existing experiment. So let me use the existing experiment. So click on next. Click on next. Runtime settings, we already have the compute instance. So you can see my compute instance is running. This is the one that I started now, right? So the one that I started, it's already running. It's a very basic machine with 4 CPU cores, 16 GB of RAM. It's a basic instance and enough for us to see a demo. So click on next and click on review and submit. So once I do that, this is the authoring part is done. So pipeline job is getting submitted and this will run behind the scenes. Okay, so now you can go to job details and you can see the flow of your pipeline. There are lots of steps. Okay, these are some of the most common steps will be visible here. Now, in case you have a question that okay, I want to do something more. I want to do something differently. I want to do something extra. Possible. You have something called Python language. Okay, so let's say there are some features that you see are not available here. Then you can absolutely use a Python script. You can define a Python function, and inside the function you can write some commands, and you can use a Python script. You can drag and drop a Python script here. Okay, so you can connect the Python script, input, output, all that you can do. So very powerful stuff. What it can do and all that stuff, right? So where did that go? Okay, let me just remove this one. All right. So now let me take you back to the view details tab. View details tab is where you can see the execution. So this is the authoring part, and this is the jobs part. The jobs part is where you can see how the pipeline is running. So you can real time see the pipeline, how it is running. And you can see the green part is it's running right now. Okay, and it's a very, very simple drag and drop method of creating a machine learning solution. Okay, you can see the green means that it is executed successfully. Okay, and this is executed successfully. And yes, I mean, it's a kind of a hybrid approach. It's pick and choose whichever one you like to do. So maybe some part of it you can code, some part of it you can put in a pipeline. It's very easy for debugging. Let's say if you're trying to, if you're having a very complex workflow and you want to do it in phases, it's very easy to debug. It's very easy to debug which part went wrong, and you'll see a cross arrow if getting errors. So the GUI part is very nice here, actually. Okay, so we'll just wait for this pipeline execution to complete. And while this happens, let me take you back to the notebook section. I told you the notebook part. Now that the kernel is active, you can see the compute is running. See, the compute is running now, and we can choose the IPython kernel, and we have a ready Jupyter notebook environment that we are comfortable with. Can you see tick mark successfully executed? This is the kernel that you can choose. Okay, so same to same stuff, no difference, no difference. Exactly what we covered. So same things you can actually go and do. And finally, the last part that you have here is something called automated machine learning. This part is really cool. And here, what you can do is you can build a complete automated workflow where the entire machine learning will happen automatically. So all this while over the course of the last few days, we talked about how you can take a data, how you can, do some pre-processing, how you can try out different algorithms, how you can try different models, and you can build something from scratch, right? So that's the approach that we covered in detail. But in AutoML, what you all you do is you just take the data and you ask the machine to do everything for you. You don't need to do anything manually. So the machine will build everything for you. And that is what automated machine learning is all about. You can say, I think my pipeline job has succeeded. You can let me just show you parallelly, then I'll come back to AutoML. So you can see the job details. And if you see it's completed, you can see all are greens, and you can scroll all the way down to evaluate model, click on preview data. And this is the best part. You can actually see the data previews that are coming at each and every step. So what is coming out of here? What is coming out of here? You can see the preview of the data. You can access your data at every step. So right click, click on preview data, click on evaluation results, and you will be able to see the uh, the typical evaluation results that we have in the classification model. So we can see the confusion matrix, we can see the classification report. So all of those kinds of things we should be able to spot right now. Okay, so this is the overall thing that we will be able to see. And finally, when we go to design the AutoML, this is what I was mentioning. So very straightforward. You can create an AutoML job manually, completely at your end. You can do that. So I already had one that I ran for a long time. It took a long time to run this. I'm not trying to do it again from scratch, but it's quite straightforward. You just say AutoML job. I just trying to show you. I'll not run this. I'll just try to show you the basic settings, what are needed, what are the things that need to be done. I'll just briefly show you. So select existing, right? Click on next. You select your task type. Task type will be classification. You select iris demo. This is my data set. And task settings, you can give some settings. You can specify what is the target column. That's it. And you can specify other parameters. Like if you want some further featureization settings, you can set that hey, I want to do this. I want to do these features, all that. You can do that. It's just all point and click. Can you see? So train test plate cross validation. You can do all of these things, right? You can say how many cross vals you want, or if you want to leave it as default, you can make it automatic. It'll anyways do all that for you behind the scenes, right? So click on next, and now you can specify the kind of compute instance that you want to create. Okay, I think this is the set of serverless computes that you can have, or you can choose your dedicated compute instance. You can either choose a serverless compute, or you can use a dedicated compute instance. In my case, I already have one. So click on it, and I can choose this compute instance, and I can basically, so I can go and I can click on next, and then I can just submit a training job. So once I do this, it will run for a long time. It will run for a long time, and at the end of the process, I will see the completed status. Okay, so 6-7 hours it might take to run this. This I already created some time back, and I wanted to show you how it looks like. So I just wanted to show you how the AutoML job, the completion looks like. You can see experiment timeout reached, hence experiment stopped. So the timeout was 6 hours. So it ran for 6 hours. Can you imagine Iris dataset so basic? And it took 6 hours to run for Iris. You know why? Because it's trying out all possible permutation combinations. That is what it's trying to do behind the scenes. So behind the scenes, we know Iris is a very simple data set. There's not much to do, but it actually tried out all possible permutation combinations. It tried to pre-process the features in different ways, do scaling, do transformation, create additional features, perform a lot of mathematical transforms on the features, try different algorithms. It tried hundreds of different algorithms, thousands and tens of thousands of different hyperparameter combinations. It tried deep learning. So it tried all the different pre-processing methods. And at the end of 6 hours, it is giving me the best model. All of it is automatically done. And if you want to see, if you want to monitor to some extent the iterations, you can scroll down and you can see which time. This is the iterations, how much time it took to fit iteration number 0. So I think it did 251 iterations. You can see how many iterations, how many tries, how many different combinations it did. The 251 different models it built behind the scene. And for every model, you can actually monitor. For every model, you can monitor the amount of time and the accuracy. So these are all the different algorithms that he tried behind the scenes. Some of which are very familiar, right? You can see this is our XGBoost. This is our extreme random trees, random forest, light GBM, KNN, right? Logistic regression, SVMs. Okay, so this is it's trying out all of these things behind the scenes. All the different hundreds of different algorithms it's tried behind the scenes. And for every execution is giving the scores. See the scores we are getting, and it's very high. Needless to say, it's very high. It's close to 100%, 99%. The scores are very high. So these are the scores we are getting actually, and this is the final end result that we will get. And whatever the final model is, you can see the model, the best model. Output name is the best model. So the best model will be saved here. Okay, you can click on this spot. The best model will be saved here. This is the best model, and you can go here and you can see what is the best model summary. The best model summary will be this. Sparse normalizer with a random forest worked the best. For this data set, this particular combinations work the best. And you can see exactly what this is, exactly what is going on, and exactly what it did. You can see, you can click on this option and it will tell you that what this is, what are the hyperparameters, and this is the entire hyperparameters that worked the best. Okay, remember manually, if we had to do this manually, we would have we would have kind of how do I put it? We would have had to write the code. We would have had to write the code behind the scenes, but you can clearly see how it is how it is doing this behind the scenes actually. Okay, anyways, so okay, and there's also an option where you can click on view generated code, which is what you see I did here, and I can see the entire code, how what was used to generate this. Okay, obviously the algorithms are proprietary. Microsoft will not release it. Okay, obviously how we did the AutoML is very confidential, it's proprietary to Microsoft, but you can actually use the services. So whatever I did with the GUI, if you want to use it in a Jupyter notebook or use a Python interface, you can absolutely do it. You just need to connect to the ML client. You can use your subscription ID, your username, password, credentials. So all that is basic endpoint access you can do. You can give your subscription ID, and you can use you can use your local collab, even Google Colab, or your local runtimes you can use to connect to the Azure client. And once you do that, you can absolutely leverage your compute. You can give your compute name, your cluster name, and on the basis of that, you can run your script. Okay, all that you can do. Anyway, so once the model is created, once the final model is created, what I can do, I can deploy the model. So you can see that the last part that I have here is register model. So whatever best model I have, this is the best model, right? So whatever best model I have right now, so I can absolutely go and register the model. This is the best model that I was able to create. So we can absolutely go and create register model. And I can also try out something called responsible AI, where we can use different methods to explain the different outputs that the model is giving. Okay, so you can click on register model. You can give it a name. You can give it a basic name, or you can do it from here also. So in the AutoML section also, you have an option to register model. So you can click on that, and you can choose ML flow. Okay, you can do it like this, or you can do it from here. You can click on this, and you can click on register model. And once you do that, you can give it a name. You can give it a basic name. I'll call it demo, and click on register. And once you do that, the model will be registered. That's it. This is the model that is created. It's a ML flow type. And if you scroll to the model section, you can see the models is created. Can you see? If I click on model, you can see the model is created today. Today it is created. The demo is the name that I gave. And you can do all sorts of stuff. You can do model versioning and all those kinds of things, right? You can see created on May 20th and whatever the date is right now. Okay. And why is it important? Why is it important to version? Why is it important to have these the model versioning? Because remember I talked about model retraining. Okay, I talked about model retraining where I mentioned that it's very important that whatever data that you're using today, the data will keep changing, right? So whatever model that you created today will need to be modified. It will need to be constantly retrained. Because if tomorrow you have some fresh data, if tomorrow you have some new data, you will need to retrain the model with the fresh data. You cannot use the same data and because that model will not be relevant anymore. Okay, that model will no longer be that model will no longer be relevant anymore. That model will no longer be relevant anymore. So what is important now is to go and take the fresh incremental data. So whatever fresh incremental data that you're getting, you please take that. And using the fresh incremental data, you want to retrain the model. You want to create uh, another model, and you save it as a fresh version. And this you will have a typical frequency every monthly, weekly, fortnightly. You might want to create different models. Okay. Anyways, the list of models will come here, and you can click on the model, and you will see the attributes of the model. This is when the model was created. If there are any versions, you'll be able to see the versions here. So right now there is only a single version, but you can see all the different versions and all that here. And once you have the model, what you can do, this is the part, right? This is how you can save a model. In Azure, it is very easy, right? This is very easy in Azure. It's all done in the same machine learning studio environment. So it takes the data, you can build a model, right? Here I did it using AutoML, but you could have done it differently. You could have done it in a notebook, and then you can deploy it in the same interface. The concept is important. Once the model is built, I can register, I can save it, I can save it in the model artifacts, and I can use it. Using means deploying, right? You can create a real-time endpoint and you can deploy it. So I can say endpoints, or okay, I can say endpoints, and you can see this is the artifacts, by the way. Artifacts is telling you the model. This is the pickle file I mentioned. Remember, I told you that how we can save the model in a pickle file. So this is what is automatically created. If you're doing it in Python, you will have to do it manually. You will have to take that model and you will have to explicitly save it in a pickle format for use it later. But in Azure, it is all getting automatically done. Okay, and then you go to endpoints and you can click on deploy model. And once you click on deploy model, you'll be able to kind of create an endpoint, and endpoints will be visible here. Okay, so you can actually create a real-time endpoint. Click on use the model. You can create a or maybe a web service. Okay, or you can create a kind of a batch endpoint, whichever way you want to do it. And this is a separate instance that you need to create for the VM. Okay, so all this we will have to do. So you need to create a separate endpoint for the this one also. Okay, that's the way how you can create the deployment. All right, so this is just to demonstrate some of the core ideas of Azure. And once you create the endpoint, it will be visible here, by the way. You'll be able to see the endpoint here. Okay, endpoint will be visible here. So I can show you, I can create one. Let me see. So you can go and create the okay, so this is the new endpoint I'm creating. Okay, I can choose the model. The model is demo, and deployment. I can just give it some sample names, and I can choose the compute. Okay, you can choose a compute cluster. Okay, and you need to create a compute cluster for this, by the way. So once you do it, you'll be able to create the endpoint. Okay, all right. Then there are other things like monitoring. So you can also add a monitoring pipeline. And monitoring is very important if you want to track how your model is doing in production. Okay, so all these are again very basic, very simple. Like a couple of videos you can watch to get a sense of how these things are working. Very, very basic interfaces inside Azure you get. Okay, there are separate libraries that you can use for it. Okay, so but you can do all these things inside Azure. And a couple of very, very important terms that are getting used is drift. What is the meaning of drift? Drift means change, right? Drift means change. So let's say you take some data today and you build a model. The accuracies that you're getting will constantly change over time. So whatever model you built today, with time or as time passes by, the accuracy of the models will change. Because the data is changing, right? So because the data is changing, the model will also constantly keep changing. So whatever model you built based on the previous sample data, so whatever model that you built using the previous sample data will have to be changed. You have to keep up with the trends. And that is exactly what production monitoring is. So if you're looking at, let's say, network intrusion prediction, it's a very standard classification problem. You're trying to predict whether a threat happened or a threat did not happen. Typically binary classification you're trying to do. And you used data from, let's say, 6 months back. And you deploy the model. Fine, all is great. Your model will give very good performance in the initial phases of your deployment. But as time goes by, what will happen? As time goes by, newer threats are emerging. Newer kinds of different types of intrusions are happening. And when you train the machine learning model, you did not train the machine learning model to identify those kinds of incursions or those kinds of intrusions in the network. So your training data itself did not have those kinds of examples, right? Because supervised learning is only as good as the kind of data that you're using for training. So your initial models did not have that kind of data. So that is why when you build the model and when you deploy the model in production, it is unable to identify those kinds of threats in production. So in the production, it is unable to identify those similar kinds of threats. That's the issue. So that is why it is very important to monitor data drift, prediction drift. So we need to figure out what is the change in performance. During deployment on my testing data, when I tested in my production, in my development environment, I was getting 99% accuracy, the same way that we discussed, right? CV accuracy or uh, initial testing that we did, we got a very high result. But over a period of time, as the model is uh, working on real production data, we will monitor it on a week by week basis, fortnightly basis. We will see what kind of results we are getting or how the model is working on real production data. That's the use case. That's the use case. Okay. And then finally, we have got data labeling services. We can also use data labeling services. I mean, and I know we took data labeling very much for granted because we were just working with data that was given to us. A CSV file was given to us. And I think as we get to deep learning, computer vision, we will see a lot of pictures are given to us. But in a real world scenario, many of the times you will need to create your own data. See, these are the reasons why the projects extend over time. Otherwise, by now, whatever we have covered in the sessions, you would have got an idea that building a sample POC is very easy. There is nothing. You take a data set, split into train test, and getting a basic baseline model it will take a few minutes. There is nothing involved. Yes, and the effort that you need to put in now is you need to pre-process your data, clean your data, you know, tune hyperparameters, make the model better. But getting a baseline is a matter of minutes, right? Once you have the right data, getting a baseline is very easy. Now, how do you make it better? How do you go back to your data? How do you curate more data? All these are the kind of things that will take time. Okay, so this is just to give you an idea to you of the machine learning studio interface. I'll start off with the discussions on deep learning. We'll understand what is deep learning, what is neural networks, and some of the related topics. So we'll start off with the foundations of what is a neuron, what is a neural network, what is deep learning. After all of what we have seen generally in machine learning, we will look at the ideas of deep learning. So the concepts of deep learning go back to the early 1950s. And this is when the term neuron was first coined. So everything in deep learning starts with this concept of a neuron. So what is a neuron? A neuron is like a computational unit. A neuron is like a computational unit which takes in multiple inputs. It does some pre-processing and it gives some output. So this is what a neuron actually is. A neuron is a computational unit which takes in multiple inputs. X1, X2 are the two inputs. You multiply those inputs with some weights, do some kind of computation, and then generate the output Y. This is what a simple neuron or the perceptron model actually is. So the perceptron model was initially proposed by a person named Rosenblatt. It was called Rosenblatt's perceptron. This goes back to the 1950s. Very, very early concept. And it's a simple computational unit, and it's a simple linear model. When you compare the simple perceptron model and the linear model side by side, you will see that they are strikingly similar. On the right hand side, this is a simple linear regression model, something that we have already discussed. We have already talked about in our very first day. On our very first day, if you recall, advertising, concrete, all those case studies that we did. So what is this linear model? Uh, what does this linear model do? We have multiple inputs, x1, x2, and we want to predict what is the output y on the basis of that. So based on these input x's, we want to predict what is the output y. And the computation that we will do is y equal to m1 times x1 plus m2 times x2 plus c. So that is the computation that we will do behind the scenes. So m1 times x1 plus m2 times x2 plus c. This is what we will do behind the scenes. The same way, even in an artificial neuron, the computation that we are doing is strikingly similar. That is why this is a linear model. You are taking the input x's, you are performing some mathematical computation, and you are generating the output y. The computation is strikingly similar to a linear model, and the only difference is in the terminology. Instead of m and c, slopes and intercepts, we use weights and biases. So we say w1 times x1 plus w2 times x2 plus bias b. This is the sum of products computation that we are doing, and we represent the whole thing as wx plus b. So weights and biases is what we basically call it. So one of the first things that I want to start out with while discussing this concept of a neuron or a perceptron is that it is a linear model. It is fundamentally a linear model where you have some inputs, you do some computations, and you get an output. Now the concept is if you have more difficult problems that you are trying to solve, right? You go back to the concept of the decision boundary and like those best fit line and the surfaces that we talked about when I was covering overfitting, underfitting, and all that. You will remember that I mentioned that linear models will not be able to represent all the complex patterns in your data. In other words, in the real world, data is not always linear in nature. Data is always non-linear. The patterns are always much more complex. So by building a simple linear model or by using a simple artificial neuron or a perceptron, we cannot represent the complexities in our data. So this simple equation cannot help us in accurately predicting y from the x's. So what is the solution? What do we do at a high level? We try to stack multiple neurons one on top of each other. We don't take a single neuron for our problem, but we instead take multiple neurons. We take a stack of many, many neurons together. And when we take multiple neurons together in a stack, we end up getting what we call a neural network. Or it is also called a multi-layer perceptron. We don't use a single perceptron, but we try to take multiple layers of perceptrons. We don't take a single neuron, but we take many, many neurons in a network, and that is what we call a neural network. And it is what we end up getting as a non-linear model. We don't get a single linear model, but by stacking many, many linear models in a network, we end up getting a very complex non-linear model. So that's exactly what a neural network does behind the scenes. And in a way, it's an ensemble. The idea of neural networks is like an ensemble. That is what makes them so powerful. So this is to give you a very high level understanding of what a neural network is. Now we'll get deeper into the conversation. This was level 1 discussion. Level 2, we'll go to the algorithm. We will go to exactly what is happening and how the neural network is actually getting trained. In other words, how the neuron is actually getting trained. We will look at concepts like forward propagation, back propagation, gradient descent, very mathematical topics, but I will give you some idea. And from there, we'll look at a series of interesting hands-ons. But before we go further into the conversation, what I want to do is I want to play this beautiful video for you. This was a video that is given by a person named Andrew Ng. He's a very popular figure in the community. So turns out there is a course in Coursera called AI for Everyone. It is a very non-technical course and it explains deep learning in a very simple way. And what I want to do, I want to take a minute for all of you so that everybody in the audience understands the idea of what deep learning actually is. And then we will take it forward from there. Let's use the So I'll just play this video. It's a small 7-minute video that I will play for all of you. And once this is done, I will discuss about the other concepts. So what we'll do is we'll quickly try to summarize the idea of a neuron and a neural network through these two beautiful examples that were quoted by a person, ONG, which all of you heard right now. So what Andrew tried to explain here is he first took the example of a demand prediction use case. So price variable, and based on the price input variable, we are trying to predict the demand. This is just like a standard linear regression kind of thing that we have already talked about. It's like taking the TV advertising value and trying to predict the sales. Okay, so and you can do it using a single artificial neuron. You can use a very simple network. You can use the price to predict the demand. Okay, this is a simple neuron. So then we went to a slightly more advanced problem. So then we said, okay, what happens if there are four features? What if there is a price, there is a shipping cost, there is a marketing, there is a material. So there are four input values available. And based on the values of these four inputs, now we want to predict what is the sales. So what is the demand? So now we want to do the demand prediction based on four features. We don't have a single feature, we have four features. And how this network will look like is somewhat like this. So you will have your price, you will have your shipping cost, you will have your marketing, you will have your material, and this is the neuron. This is where the demand is going to be forecasted. Okay, so the demand is basically a function of all these four input features. Okay, and we can denote these four input features using x1, x2, x3, x4. So we can say this is x1. So we can say this is the x1 feature, this is the x2 feature, this is the x3 feature, this is the x4 feature, and based on this we want to predict what is the demand. Now, how will the equation look like in the context of neural network? A simple artificial neuron. Remember, I told you a neuron is like a computational unit. You will give it some inputs, it will do some processing, and on the basis of that, it will give some outputs. It will churn out some outputs at the end of the process. So the computation that will happen here is it will take each of the inputs, it will multiply by the weights, it will add a bias, and it will predict the value of y. Okay, and there is one additional thing that we do here is called activation, which I will talk about later. But at a very high level, we are using this equation to take the initial weights, multiply with the feature values, add a bias, and that is how we get the predicted value of y. Okay, and there is another additional thing called activation that we also do. So we don't quite exactly take this output value. So we calculate this equation expression, and then we pass it through one more layer called an activation layer. There's something called neuron activation that we do, and based on that we get the output. This is the simple way how we understood things so far. Now the problem is, if you look at a real world scenario, the output does not directly depend on the input features. Like if you look at this example, the output demand does not directly depend on the input price or the input shipping cost or the marketing or the material. The output price doesn't directly depend on these factors. The output price seems to have an indirect relationship with these factors, but it does not have a direct relationship with these factors. Because that is what we are trying to predict, right? We are trying to predict what is the output demand. So based on all these input x's, we are trying to estimate what is the output. So the output will not have a direct relationship with any of these input factors. It will have an indirect relationship. So think about it. If I give you the price of a product, can you really say that if the price increases or the price of the product decreases, is the demand impacted based on the price? So imagine if the price of the product decreases. If you reduce the price of an item substantially, let's say some offer is going on, and the price of an item is substantially reduced. So if a price of an item reduces, the demand increases. But is it because the price reduced, the demand increased? Correlation, right? It's a correlative. So that means price is correlated with demand. But if you think of the causation, maybe because the price reduced, something else happened. Maybe there is some other kind of intermediate features that are playing out, right? And that is where Andrew talked about the concept of hidden layers. That is exactly what the hidden neurons actually are. So the next part of the conversation, we will see the hidden neurons that he introduced in the process. So he said that price does not directly cause the demand to increase or decrease. Shipping cost does not directly cause the demand to increase or decrease. And that is true for all real world scenarios. Whatever observable features we have, the output is not directly impacted by the observable features, but it is indirectly impacted. So then what we have to do is we have to create an intermediate layer to identify what those indirect features are, hidden features are. What are those latent features that is actually causing the demand to get impacted? And that is what deep learning is trying to find out. That is why we call it deep learning. The term deep in deep learning means, yes, it is still a subset of machine learning. Yes, you're still trying to learn the association between input X and output Y, which is what was talked about all through the video. But what you're in a way trying to do is you're trying to learn the deeper features. From the original input X's, can we find out what these hidden features are? What are these hidden features which are allowing me to find out a good association between the input X and the output Y? And then we enter into the conversation of the hidden features. Then he talks about what those hidden features actually are. So here we took an example of affordability, awareness, and perceived quality. And later on, we say that, okay, these features, this is just given as an example. But in reality, you cannot define the hidden features because we do not know what these hidden neurons are because they are latent features. We cannot explain them in a simplistic manner. Okay, it is not interpretable. Unlike the original features which you know, it is your data, so you know what your features are, right? So the original features you know, but the hidden features you will usually not know. We will not know what these hidden features actually are in practice. Okay, so from the hidden features, now we can go and estimate the demand, and you can see that we are able to draw a very good relationship here. Okay, and the hidden features are derived from the original features. Okay, and this is the indirect relationship that deep learning is trying to uh, find out. Okay, there is no direct relationship between price and demand. It's a correlation, but we are somehow trying to figure out the causation. We will never know that for sure, but we are somehow using hidden features to really unearth those latent factors that are actually causing the demand to increase or decrease. And this is the last part of the video where Andrew talks about the fact that these features really don't mean anything. They don't mean anything. They're just hidden features. They're hidden neurons. Okay, so from the original set of neurons, we are able to derive a set of hidden neurons, which mean nothing. They're just mathematical equations. They're just some combinations of the original inputs that you're getting this value, but in reality, it means nothing. And in all of deep learning, what are you fundamentally trying to do? You're fundamentally trying to find out the relationship between the input X to the output Y. Okay. So back to the core ideas of supervised learning. You'll have lots and lots of labeled data. You'll have lots and lots of input X's. You'll have lots and lots of output Y's, and all that you're trying to design the architecture. So when we introduce TensorFlow Keras, we will see how you will design the architecture. As part of the architecture, you will specify that, hey, I will have this many input features. I have this many outputs that I'm trying to predict. You have to define the architecture correctly. As part of that, you specify what is the input, what is the output. You design the architecture accurately. And as part of that, you have to also specify how many hidden layers you want to have. how many hidden layers you want to have, and in each of the hidden layers, how many hidden neurons or how many hidden features you want to have. The two things you will try to do. One is you will try to identify how many hidden layers you want to have. And in each of the hidden layers, you want to identify how many hidden features you want to have in each layer. So you design the architecture, and then it's a process of the neuron training, the neural network training that you will do, where you will try to fine tune the network in such a way that it is able to accurately find out the associations between the input X and the output Y. And this is the part that I will talk about a little bit more in detail, how that training happens, what is forward propagation, what is back propagation. So we'll get to those conversations. The second part of the video was also very interesting. The second video went into the concept of, let me open it up for you. And this is a very non-technical explanation, which I think it's a good way to study because we are just starting out the discussion, and I think it was good to actually see what's going on at a very high level. The second video focused more on pictures, and we will discuss about images. We will discuss about images in detail. Computer vision is something that's planned for mostly tomorrow. So today maybe a little bit of it I will talk about towards the ending parts of the session, but majorly all through the first half we will discuss lots of advanced computer vision use cases. So that's the plan. So we look at a picture, we look at the image data, you can see, and the concept is, how do machines look at pictures? So humans will look at an image like this. How do machines look at images? Images are nothing but pixels. So images are nothing but a collection of pixels. These are all pixel values, right? So again, the same idea applies here as well. Imagine you're trying to do image classification. You are trying to look at a picture and you're trying to classify who is this person. Imagine you're trying to use it for some kind of an attendance mapping algorithm. You're trying to use this as, in the main gate, some kind of camera system is installed. And whenever anybody walks into the main gate or walks in front of the main gate, the model will automatically detect who the person is. So depending on that, the attendance will be automatically marked. So we are kind of trying to do an automatic attendance marking system. Okay, so depending on the person who is arriving at the front gate, the model will automatically mark your attendance. Let's say that is the use case we are discussing. So what are we trying to do, friends? We have a picture. Based on this input X, we are trying to predict the output Y. So this picture is extremely complex. This image is extremely complex. And this image is comprised of its base pixels, because images are nothing but a collection of pixels. So what is needed is, just like the last example that we saw, this picture is not enough. The original image is not enough to predict the output. It's very hard to predict the output just based on the original picture. So if you say this is the input X and this is the output Y, we don't have a direct association between the picture and the output. So just based on the pixel values, you cannot get to the output. So what we do, we use deep learning. And this is basically 1000 cross 1000 cross 3, because there are 3 channels. The width and height of the picture is 1000 cross 1000. So there are like, if you multiply 10 cube into 10 cube, you get a million pixels. So there's like 1 million of these small squares that you can see. Okay, and there are 3 channels because it's a RGB picture, red, green, blue. So into 3 is 3 million. So this image is like 3 million pixels. So this picture can be represented using 3 million numbers. That's the absolute raw input, right? So that raw input does not have a strong relationship with the output. You cannot predict the output class or who is the employee only on the basis of these raw pixel values. So what we need to do again is we need to use deep learning or neural nets, or specifically CNNs, which we'll study later. We will use hidden layers to identify features. So from the picture, from the original picture, can we identify hidden features or latent features from this person's face, which can help us classify more accurately who the person actually is? So this is the indirect relationship that I was trying to address. You're trying to somehow take the original data. In this case, you're looking at the original picture or the original features you're looking at. And on the basis of that, can I derive intermediate features? Can I derive the intermediate features which are visible? Like in this case, you can see the first hidden layer, we are able to derive some very low level features, like very basic features like, okay, diagonals, lines, color patches, shadows, backgrounds, reflections, and those kinds of things. Maybe color, all those kinds of very, very basic features we are able to decipher from the first hidden layer or the initial set of hidden neurons. The second hidden layer neurons we are trying to uh, build up on the first layer, and we are trying to find more advanced features. So the second hidden layer, we are building up on the first layer, and we are trying to find more hidden features. We are trying to find more hidden features in the second layer. So we are trying to build on the intermediate in the initial original set of features, and we are trying to create hidden features. We are trying to create more advanced features. We are trying to decipher, hey, do we see the eye? Do we see the nose? Do we see the cheek? Do we see the mustache? And things like that. And the third hidden layer, the final one, we are actually combining all the previous features, and we are trying to create more advanced features. So as we iterate through the neural network, we start with basic features and we try to build on top of it to create more and more advanced features, which we think can help us predict the output more accurately. So back to the original discussion that we had with all of you. You have input X, you have output Y, and you're trying to find this relationship. Can we identify intermediate features in between which can help us do that association more accurately? To start with basic features, use the neural network to generate more advanced features. That's why we call it deep learning, right? We are trying to create deeper features. From the original features, can we create deeper features which can help us find that association a lot more accurately, right? So that's the basic idea of what we are trying to do in deep learning, right? So I hope this initial set of diagrams really helps you to understand at a very high level what deep learning is. And with this in mind, we will go back to the demo. We started our conversation with this diagram. I hope all of you recall. We started with neuron. What is a neuron? Then we took a small digression. We looked at the video description. And now let's go back and try to associate this with the actual process of how the neuron is learning. How is the neuron learning? How is the neuron actually learning the patterns on the basis of the data? How is the neuron training actually happening? What is going on behind the scenes? So let us take an example where we are trying to do housing price prediction. I'm taking a very simple regression example to explain the algorithm that is working behind the scenes. What exactly is forward propagation? What is back propagation? What is gradient descent? How is the network trained? And here it is a simple neuron. We are not even taking a neural network. We are taking an example of a simple neuron to explain the process of training. And then we will extend this to a bigger use case going forward. So let's say, once again, based on the input X's, square foot, neighborhood, and bedrooms, you are trying to predict the price. It is a typical price prediction use case that we are trying to solve. So based on the input X's, we are trying to predict the price. So we have square foot, neighborhood, bedrooms. So based on the square foot, neighborhood, and bedrooms, we are trying to predict the price. So we have a simple artificial neuron that we will use for the computation. We will give this as inputs. X1, X2, X3 are the three inputs that we will provide. We will multiply these input x's with the weights W1, W2, W3. We'll add a bias and we will calculate a predicted value. Okay, this is the way how we'll work it out. So again, X1, X2, X3 are the three inputs. We will feed that to the neuron. We will multiply those inputs with the weights. We'll add a bias and we will calculate the predicted value of Y. Now, if you remember in linear regression, if you just go back to that conversation for a minute, if you remember, we were trying to find the line of best fit, right? That Y equal to mx plus c, if you recall for a minute, that is the best fit line we were trying to build, right? In that entire conversation of the linear regression, we were trying to create a best fit line, right? We were trying to create what is the line of best fit. And there are different lines that are possible. If you recall that scale that we talked about, there were different lines that you could draw. So if you take a different slope and if you take a different intercept, if I give you a different value of m, and if I give you a different value of c, right? So there's actually a very nice video that or animation that talks about it. I can take you to that animation. A very nice animation that actually talks about that. linear regression process, whatever I'm trying to explain here. So look at this one, right? So you can see. So imagine this is the set of data points I have right now. And so there are infinite number of different MNCs you can take, right? If let's say this is the set of data points I have, if I want to do linear regression, I can take different C's and I can take different M's, right? I can rotate the line in different ways, right? You can see how I can take a different slope and how I can take a different intercept. So by taking different slope and intercept values, I can build different lines. And out of all these possible slope and intercept values, this is like that y equal to mx plus c. So we can try different m's, we can try different c's. And by doing that, we are trying to find what is the ideal MNC. That is the crux of linear regression that we talked about, right? Now, if you extend this to the neuron, and because the neuron is also a linear model, instead of M and C, you are trying to tune W and V, but the idea is exactly the same. Just like here, we are trying to adjust and we are trying to take different M and C values. Similarly, here you are trying to take different weights and bias values. So the end result of a neuron training is we are trying to narrow down to the best possible value of weights and the best possible value of bias. We are trying to find out what is the ideal weight and what is the ideal bias. That is what we are trying to do. What are the weights and biases of the neuron? But obviously, when we start the training process, we will not know that. We will not know what is the weights and what is the bias right at the outset. Right at the start of my training, we will not know. We will not know what is the weight and what is the bias, right? So what do? We start with random weights and biases. So right at the start of the neuron training, we start with a random value of W and a random value of B. And then we do something called forward propagation. What is forward propagation? Forward propagation means you're going forward. You are taking those weights and bias values that you initiated. This is step one. Step two is this. You use those weights and bias values to calculate the Y predicted. What is Y predicted? W1 X1 plus W2 X2 plus W3 X3 plus bias B. This is the predicted value of Y that you're getting from those initial random values. So you add the predicted column here. I'm just trying to demonstrate here for you. So now what you do is you calculate the loss. So you're saying, hey, I took some random weights and biases, and using those random W's and B's, I'm seeing how my network is doing. That means if I had used those weights and biases for the computation, my predicted values would have come like this. Are they similar to the actuals? Please calculate a loss. Please calculate a loss. Are they similar to the actuals? So you will calculate a loss. You will calculate MSE loss, MAE loss, the different loss functions that you have. And you will see some loss, right? The predicted will never match the actuals. You will see some loss. There'll be some delta, the error. And then you will do something called gradient descent or backpropagation. Now, what is gradient descent? Explaining this in very simple terms, gradient descent is the process of updating the weights and biases. Simple, straightforward. You got some loss, right? You saw that, okay, the predicted is not matching the actuals. Step one, you took random W's and B's. Step two, you calculated predicted value. And step three, you see the loss is pretty high because naturally with the random values, it will never match, right? The loss is very high. With those weights and biases, I am not getting the right predictions. My predictions are far from the actuals, far from the actuals. So I will do gradient descent and I will update the weights and biases. This is called backpropagation because you're going back and you're backpropagating and you're updating those initial weights and biases that you took. So you update the W's and B's. Then with that updated W and B, you again do forward propagation. You again calculate the predicted value with those updated W's and B's now. And naturally, this time it will be little better. It will be little better, right? Because you did something. You went back, you updated the weights and biases, you did something. And based on that, when you recalculate your loss, the loss would have reduced a little. It's like we all make incremental improvements in our life, right? We all start with something, we make lots of mistakes, and then somebody gives you feedback. So think of this gradient descent as a feedback. So when you get that feedback and when you fine tune those weights and biases a little, the next iteration, your loss would have reduced. You would have been slightly better. But then there is still some loss, right? Again, what do you do? Again, you go back propagate, update the weights and biases. Again, using those updated weights and biases, you calculate the predicted value. Again, calculate loss. The loss would have further reduced, right? But it still is there. So you keep doing this over and over and over again. And each of these cycles is called an epoch. So what is an epoch? An epoch is like a cycle, right? It's an iteration, right? It's an iteration. So one forward propagation and one back propagation cycle together is called an epoch. So you continue doing this for many epochs until your loss becomes stagnant. Your loss minimizes to the point where it no longer reduces further. And then there are other kind of things like training loss, testing loss, which I'll come back to later. But this is the core idea how we train a single neuron. The idea is extends the same for a neural network also. This is a single neuron. So you start with random weights and biases. You find out the predicted value. You compare with the actuals. You calculate the loss. And then you do gradient descent, where you go back to the previous steps and you update the weights and biases. And you keep doing this over and over and over again. And with every gradient descent, with every weights and bias update that you do, you make the network slightly better. So now when you update the weights and biases, your predicted values will be slightly closer to the actuals. It'll be slightly better. The loss will slightly reduce. So that's the assumption we are making. By making small incremental changes, by making small updates to the weights and biases, by giving that small feedback, think of gradient descent like a feedback. So by giving that small feedback, we are able to make the network better. And that's what we try to do in deep learning at a very high level. So next time you hear about an algorithm called backpropagation, somebody talks about, there's something called backpropagation algorithm. This is exactly what they're referring to. So this is the backpropagation algorithm that is working out behind the scene. Now this is a slightly more technical. I would say, this is the level to the technical, depiction as to what is going on behind the scenes. So I'm not going to get too much into this topic, but at a very high level, if people can relate to it, I'll just briefly walk you through it. So this is the thing. You can see this is the neuron. This is the input x's, weights W1, W2, B, and this is the computation that we are doing. Okay, and you try to find out your weights and biases such that MSE is minimized. MSE, we are dealing in the context of a regression problem. You are trying to minimize your mean square error, and this is the loss function for mean square error. And if you take a look at it, this is actually how the weights and bias updations are happening. Again, start with random W and B, forward propagate, compare with actuals, calculate loss, and update the weights and bias. This is the formula for backpropagation. Okay, so the new weight equal to old weight minus eta times some change, and the new bias equal to old bias minus eta times some change. Okay, now this formula you can completely ignore. It's not that relevant right now. But what is important, the key learning from this particular slide is this part called eta. Very important. We will discuss this in a lot of detail as we go along, as we train neural networks. Eta is a very important thing. Eta stands for learning rate. Okay, so what is its eta stand for? Eta stands for learning rate. So as we come to the hands-on exercises, we will see how we can use eta going forward. And using eta, you can tune how the network is learning. You can tune the network training in a lot of detail. So just to give you some context, if I say eta equal to 0, we'll take an extreme case. If I take the learning rate to be equal to 0, zero learning rate means what? That means no learning is happening. If I take the learning rate to be equal to 0, zero learning rate means there is no learning that is happening. That means the new weight is equal to the old weight. So here, if you take eta equal to 0, that means the new weight is equal to the old weight. There is no change in the weights. And if you take learning rate equal to 0, the new bias is equal to the old bias. So the weights and biases will not get updated. That means there is no learning happening. So learning rate 0 is very bad, obviously. The whole idea, the whole success of gradient descent, the algorithm lies in updating the weights. You want to update the weights, right? You want to give feedback. You want to make those small improvements. If you're not updating the weights only, then how will the learning happen? Nothing will happen, right? The learning rate 0 is bad. On the contrary, another important thing is a very high learning rate is also bad. So as we start doing the demos, you will realize that whenever you set a very high learning rate, the network doesn't train that well. Because if you set a very high value of eta, the changes will become too unstable. There will be too many, too many random, too big changes that will happen. Okay, so it's like saying that if your eta is a very high number, then W new equal to W old minus this, right? If this number is very high, the updates will be too big. And this is again a general concept in deep learning at a very high level, that we should try to make small updates, not very big updates. So as you update your neural network, as you update the weights and biases in your neural network, try to keep the update small. Don't make it 0. 0 means there is no update you're doing. At the same time, learning rate should not be too high, because if you make it too high, the updates become too big. You dump too much. Like, it's like sometimes you learn something, sometimes you learn something else. So you learn too fast. Even fast learning is bad. Too fast learning is bad. So try to make it moderate. So typical, very good default for learning rate as we come to the demos will be something like a 0.01, something like a 0.1. You should definitely take a learning rate always less than 0.1, always, generally. It's a good default. Okay, and certainly, I mean, most use cases, you will see the learning rate is always less than 0.1. So 0.01, 0.001, these are some very common learning rates you will find. So we always try to make small incremental changes. Okay, so this is the important concept. And then obviously, like, this is the concept of how the backpropagation algorithm works out. Whole bunch of theory, but I hope everybody has the general concept now. And this is another very nice presentation which I used to explain the idea of learning rate. So you can see right now, if we take a very high learning rate, this is exactly what I explained a while back. If we take a very high learning rate, what will happen? The loss will not come down. The loss will not come down if my learning rate is very high. So if my learning rate is very high, the loss will not come down. You can see right now, the loss remains high because you are making too many changes. You're taking too big steps. Like, getting it, like, it's like saying, if you're learning some topic for the first time, I'm giving very broad feedback. Okay, hey, do this. Okay, let's say you're learning deep learning for the first time, and I give an exercise to you. So I'm simply giving an exercise, and without explaining any of these topics now, I say, guys, this is an exercise, please solve it. Will you be able to solve it? Of course no, because most of you are beginners to deep learning, right? Think of it that way. So learning rate high means you're giving, like, we're making a rapid step, rapid jump. I'm just telling you, okay, do this. I'm not giving you the detailed guidance or the detailed teaching. That's a very high learning rate. So you will not learn anything. Loss will remain high. But on the contrary, even low learning rate is very bad. Low learning rate means we will end up teaching the topics fine, but it will be like 5 years before we complete deep learning, right? That's what some of the universities do. The same stuff they are teaching for 5 years. You will do one module, and then next 2 months you will do useless exercises. Some quiz, some absolute useless MCQs and all they will do, right? That is how they stretch the course for 5 years. On a lighter note, obviously. Anyways, so if you have a very low learning rate, if you take a very low learning rate, what happens is you are learning very slow, very slow. So that means the loss will reduce, but the loss will reduce very, 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 very slowly. The objective of a good learning rate would be something like this, something like the green. And there are ways to plot it out. I'll show you how to plot these things. Right, so there's very nice. There's some TensorBoard callbacks and all we can use to, visualize the learning rates and how taking different learning rates you can. So you can think of learning rate like a hyperparameter. We talked about hyperparameters in machine learning. They're like tuning knobs. Remember how different machine learning algorithms, we use tuning knobs like maximum depth and estimators. Okay, we can tune the hyperparameters. They're like tuning knobs. So same way you can think of in deep learning, learning rate is a hyperparameter. You will typically try out different learning rates and find out the one that works best for you. And the optimal one is this. So you want to take a learning rate A good learning rate is one where you drop very fast. So you learn very fast initially, and then from there it's a gradual training. So I don't want to take forever to teach you like the basics. So the basics we learn very fast. I mean that's the hallmark of a good training, right? You learn the basics very fast, and then we take enough time to fine tune the concepts and do lots of exercises. And this is the thing. So there won't be too much of a reduction of loss here. It becomes a little stagnant, but that's the thing. That's the concept of a good learning rate. Okay, so I hope everyone's clear. So we talked about what is the neuron, what's a neural network. We understood backpropagation. We understood the gradient descent algorithm. What exactly is gradient descent? What are we doing? And the fundamental idea in deep learning, be it a single neuron, be it a neural network, a network of neurons. So in deep learning, generally, what we are trying to do is we are trying to find the weights and biases of a network such that the loss is minimized, such that the predicted values are near about similar to the actual values, such that we are able to find the best possible association between the input X and the output Y. So going back to Andrew's video, we are only trying to find the association. We are trying to find a mathematical association between X and Y using the equation W1X1, W2X2. So at the core of deep learning, we are just trying to find out what are those weights and biases. The weights and biases of the network are what we are trying to tune and train. Okay, all right. So now we'll start off with our very first case study. And as we see those case studies, we'll get some more clarity in terms of the some of the more contents and theory and everything that we'll see. So we'll do our very first case study, and in the process, we will be using a slightly different framework called TensorFlow. So far in traditional machine learning, we have used something called scikit-learn. So in deep learning, we will be using something called TensorFlow Keras. TensorFlow Keras is the framework that we will particularly use for deep learning. So this is the Boston housing dataset. So the case study that we have is on Boston housing. So we have the different features of a particular district in Boston. And based on that, we are trying to predict what is the price of a particular district in Boston. So that's the data set. This is what we have in terms of the data set. So if you want to get a little clarity, you can Google out. It's a very popular data set. And we are not loading the data from any CSV file here. We are taking a tf.keras or datasets. You can see it's a default dataset that is built into, it's actually built into Keras. If you want to know about this dataset a bit more in detail, you can go to Kaggle, you can look it up, you can see the dataset, you can understand the features. Let me show you. Let me show all of you. This is my dataset, all of you. The Boston housing dataset. You don't have to memorize. Okay. So all that we are trying to do, we are looking at the different features of a particular district in Boston. And based on that, we are trying to predict what is the median housing value of a home in Boston. So the last column is the output column. There are total 14 features you can see, right? You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there are 13 input features. And based on 13 input features, we are trying to predict what is the output price. It's a simple housing price prediction problem that we are trying to solve. So what could be a practical utility for this exercise? What could be a practical use case for this? Well, maybe you can think of it in the context of a real estate company. You have a real estate company who which is trying to estimate prices of houses in different localities. So they're looking at different patterns, like here you can see the features like what is the population, what is the pollution levels, how far is it from the city center, how far is it from the river, right? So is it near to a port, things like that. So uh, you can see this also looking at nitrogen oxides concentration. So that is giving an example idea of the pollution levels in the locality, right? So weighted distance to 5 Boston employment centers. So if you're very close to an employment center, most likely your prices are more. But if you're very far away, maybe if you're in the outskirts or the suburbs of the city, then the housing prices are much lower. So these are the features that we are using to predict the prices of the houses. So moving on, let me run the code, and I'll be doing the demo. First one, at least I'll show you how it's working out. So this is straightforward. We are running this in Colab, all of you can see. And So first thing, we will load our data. The first thing, we load our data here. And this is my data frame. And we do some normalization. This is done for scaling because my data is in very, very different scales. This is just an initial bit of scaling I did. And what I really want to do is come to this part. This is the most important part where we are actually building a graph in Keras. This is the most important piece of code. Okay, so first time we are seeing, the first time we are actually seeing a particular graph that we are building using TensorFlow Keras. So what is going on? What is going on behind the scenes? What is the meaning of this code? So first we are instantiating a sequential model. So what is a sequential model? A sequential model is one where you have a very clearly defined sequence of steps. You have a very clearly defined sequence of steps. The output of the initial step, the previous step, will become the input to the next step. So that is how we define a sequential model. You can create different types of models in Keras. You don't have to do it in sequential. But the moment you say tf.keras or sequential, that means whatever you do, whatever you add, let's say you say model.add, model.add. So all of these are getting sequentially added. Imagine it's like a, it's like a kind of a stack. You're creating a stack. So first you add this layer, then you add this layer, then you add this layer. So you're stacking multiple layers. This is what we call a sequential model, right? So the very baseline model that we are creating consists of 13 input features. Okay, so we have x1, we have x2, we have x3, and we go all the way to x13. Okay, so we have 13 input features, x1, x2, x3, up to x13. So these are the 13 input features we have. And based on the 13 input features, we want to predict what is the price of the house or the median, median prices of owner-occupied homes. This is the neural network we are trying to create, neuron we are trying to create. Okay, it's a price prediction that we are trying to do. So based on the input x's, we are trying to predict the output y. And that's the network for you. You can see first we have got input 13 comma. 13 comma means there are 13 features and that's the input layer. So we are reshaping that. And then output is dense of 1. What is the meaning of dense of 1, friends? Dense layer means a fully connected layer. So what is a dense layer? A dense layer means a fully connected layer. That means the neuron is connected to all the previous layer neurons. That is what we call a dense layer. Right? So dense layer in this case means this neuron, whatever neuron you're seeing right now, this neuron is connected to all the previous layer neurons. So the output neuron price, the output neuron right now is price. So this output neuron price is connected to all the input layer neurons. That is what we call a dense layer. But otherwise, there is why is it one? Because we can understand there is a single output. We only have a single output here, so hence it's a single neuron that we are trying to predict as the output. So once that is done, now this is the architecture that we designed, and now we can define our loss function. Okay, so that's the easiest part. So we can go and define the loss function. So loss function we can we can give a default loss function, and the loss is MSE. Okay, so we can run this part, and we can also see the model summary, and the model summary is exactly what I explained. You can see there are 13 inputs and there is one output, and you can also see that there are total 14 parameters. Why are there 14 parameters, friends? There are 14 parameters because there are, what are you primarily trying to learn? You are trying to learn 13 weights, W1, W2, W3, up to W13, and one bias. So total, there are 14 parameters that you're trying to learn. Okay, so how many total parameters are you trying to train in the network? There are total 14 parameters that you are trying to train. So there is some X, there is some Y, and overall, you are trying to learn 14 parameters. The 14 parameters that you're trying to learn. 14 weights and biases you're trying to learn in the network. Okay, that's the idea. So obviously you can understand the deeper the architecture. If I add some hidden layers, which I will add shortly, if you add hidden layers, then you will have more number of parameters, more number of weights and biases. Okay, and this is the math. This is the math that is working out behind the scenes. You can see 14 parameters we are trying to learn. And weights and biases are what? What are weights and biases? This is actually float 32. right? The TensorFlow default is float 32. Okay, float 32 means what? 32 bits, right? 32 bits means 1 byte. That means every number, you're like storing 4 bytes. 4 bytes means 32 bits, right? So each number is 4 bytes. So 14 numbers, 14 fours are 56, 56 bytes. This is the amount of space you need to store those 14 parameters that you trained. This is a very, very simple architecture we are seeing. It's a very simple neuron where there are only 14 weights and biases that you're trying to tune. That means at the end of the neural network training, right? And you can see it. Let me just show the training also to all of you. At the end of the trainings, I can just go and run this model.fit for 100 epochs. And when I do that, you can see it's trying to train and it's trying to learn the weights and biases. Every iteration, you can see the loss is reducing, loss is reducing. And at the end of it all, I will get these weights. At the end of 100 epochs, I would have learned the weights and biases. And this is what you're ultimately saving. So when we say in deep learning that we train the model, a model is nothing but its weights and biases. So two things. One is the architecture. What is the architecture? Architecture is 13 and 1, whatever architecture we define, the summary. And what are the weights and bias numbers? Okay, so that part is also very, very important. Then we can save the model. Then we can save the model. We can deploy the model. Okay, so this is broadly what's going on. So this part is very important to keep in mind because, like if you have a very deep architecture, like here also, if I add some more hidden layers, and which I will do now, because very clearly you can see the loss is pretty high. Like even after we train for 100 epochs, the loss remains 400. Loss seems to be very high. Okay, so now what I will do, I will go back to the dense layer, this part, and I will simply add 2 additional dense layers. I will simply add 2 additional dense layers. So what will happen here is I have to run again from here. You can look at the model summary. It's a lot more complicated. Can you see? Because I added these additional hidden layers, I have more neurons that I've added here in between. And that's why the overall number of parameters is 2421. And the total size that this will take to get stored is how much size we will need to store this. The total size, that is needed to store this thing is 9.46 KB. So we need 9.46 kilobytes to store this entire thing. Okay, so all of you are able to get a sense of this. And you see, that's why even today, like all these large language models that we see, like GPT and Gemini, we have all these large language models that are available. In all these large language models, also like what we see, you'll typically see that they are huge language models. Several millions, hundreds of millions to billions, to several hundreds of billions to trillions of parameters. In fact, today's large language models have upwards of trillions of parameters. So what is that parameter? When you see a LLM, when you see a GPT model, a Gemini model, what is it? What is it behind the scenes? Behind the scenes, it is a neural network. It is a neural network that is trained with lots and lots of data. And behind the scenes, companies like OpenAI, companies like Google, companies like Meta, they would have used a lot of computational resources. Neural networks would have been used to train the networks. And at the end of the process, you would have learned the weights and biases. Ultimately, you're trying to learn. So next time you read an article and it says, hey, you know what? We have the Gemini model with a trillion parameters. You know what it is. You know that there are trillion weights and biases. And that's why these models are massive. A trillion parameters, you can imagine. You do the maths right now. Even if you, like, there are other efficient ways they do the computation. You do the maths. You take, this is what, 2421 into 4, right? It is taking this much kilobyte. You take 1 trillion. What is 1 trillion into 4? 4 trillion bytes. That means 4 trillion bytes. Now you do the maths right now. 4 trillion bytes means how we can even save those kinds of things. And there are different efficient ways how they do it. That's another different conversation altogether. But the idea is to educate you and tell you what is the meaning of a model parameter. When we train a deep learning model, what exactly is a model parameter? Model parameters are the weights and biases. And that is exactly what you're learning. That is exactly what you're training. When you do gradient descent, you're updating those weights and biases. And at the end of all the epochs, this is the final thing that you're trying to get. And to save it, you need space. You need memory. Okay, that's why these are very, very memory intensive applications. So let's see that after we add these two hidden layers, did my network improve? Did my loss drop? My loss was seemingly very high initially. Yes, surprisingly, it's gone better. No, remember, initially after 100 epochs, my loss was what? It was around 300, right? Can you see? Surprisingly, my loss has dropped. That's the magic of deep learning. It's not guaranteed that if you add 100 layers, your loss will be zero. It's not guaranteed. This is again a trial by error process. You will have to iterate. You will have to. It's just like a hyperparameter. You have to try different approaches, and you have to see that with which approach you are getting the best fit model. So the conversations about overfitting, underfitting, all that holds true. All the overfitting, underfitting ideas that we covered, all that holds true, right? If you have too many hidden layers, what will happen? The network will overfit. Okay, if you have too many hidden layers, if you have too many hidden neurons, what will happen? You will have overfitting. And if you do not have too many hidden layers, what will happen? You will have underfitting. So overfitting, underfitting, all those are related ideas that we have here also. So too many hidden layers, overfitting, and if you do not have too many hidden layers, it will be underfitting. So if you get the weights, let me see what the weights. Lot many weights are there. You can see very clearly. There are 2,421 weights and many weights and biases are there. So these are the numbers that we actually learned in the process. If you want to train it more, if you think that, okay, there's a scope to make it more, there's a scope to reduce the loss even further, you can try it out. Now, these are the experimentations that you can keep doing. Okay. Now you can maybe take another dense layer. You can probably take 1,000. We can maybe start with, or maybe not 1,000 will be too much. Maybe we can take 200. And maybe I can add another dense layer. I'm trying to really complicate the network right now. You can see. So dense 200, dense 100, dense 50. And this is generally a preferred way of doing it. You start with lots of features and you try to narrow down. It's generally a best practice. So now let me try this architecture. So naturally, you can see it's a deeper architecture. There are 28,000 parameters. It's a much deeper architecture with uh, 28,000 weights and biases that we are trying to train. And if we go and do this, let's see, it will be a little slower comparatively. And it will be interesting to see if it made any meaningful difference to my overall losses. Okay, and you can actually monitor. I think it's probably reduced a little, not a lot, but I think it's reaching the 28 mark, but it's fluctuating. And as we go through the conversations, we will see different callbacks to use, different checkpoints to use, but definitely I am able to touch a 28 loss. If you want to further train it for 200 more epochs, what you can do, so you can just run this code again. Don't have to run from the beginning. You already did until model.fit, just run this again. Okay, just control enter, run this again. And you can see, look at it, I got 24. So definitely, as I train it more and more, I am able to get better results. Look at this, 21, 22. I am seeing things that I did not see before. 18, 16, 14, incredible. I can train it for, maybe now I get the confidence, train it for 500 more epochs. Let's see. Let's see. If I train it for more and more duration, there is a possibility of my loss reducing more and more and more because I have a very powerful network. I have a powerful network that is stacked over 4 hidden neurons. And the more I train, the more weights and biases I'm trying to learn. You can see I'm going to single digits now. I think there was a time I saw 9 or 8 come. Okay, so it's fluctuating. See, this is 9, loss of 9. Can you see? Loss of 9 is incredible. We did not have this value before. We are seeing a loss reaching even up to 9. So previously from 500 we come to 9. So this is the demonstration I wanted to show you how you can train the weights and biases, how you can make it better, and how by iterating over many epochs you can get a very good model. Look at it. I'm even touching 8 now. I'm even touching 8 now. And maybe if you go further over more epochs, you will get even better. Even better. It's not guaranteed. It's not guaranteed that you will always do well. But generally, if you add more layers and if you add more neurons in the learning process, you will get a good model. But you will have to monitor overfitting. Okay, because remember, this is the training loss. So what you're seeing on the screen is a training loss. So there might be a possibility that the training loss is reducing. If you're building a very complex model, your training accuracies are going up. The training loss is reducing, but your validation scores are bad. So you need to add a validation loss also, which we'll do shortly. Okay, so that's something we will do. But yeah, I hope the core ideas are clear. Yeah. Mhm. I will talk about it. For now, activation, just assume there is something we have here. So activation at a high level is this, but what exactly it is going to be my next discussion. I will talk about it. But at a very high level, activation is this. Remember at the beginning, I told you that when you use a neuron, you are doing that sum of products computation and then you do something else. This activation is an additional mathematical function that you're using. So you take the initial inputs, you multiply with the weights, add a bias, and then you go and you perform another additional mathematical computation. That is what we call an activation. ReLU activation, that's a mathematical part. ReLU activation, what it does behind the scenes is something like this. This is actually mathematically, this is exactly what ReLU does. You can see ReLU stands for rectified linear unit. So this is one of the best activation functions that we use. You got it right. This is the math behind ReLU. Yeah, there are a lot of activation functions in deep learning, and at a very high level, activation functions are used to introduce non-linearity in the network. Okay, because that's the whole objective of deep learning, right? I'm not getting into the mathematical explanations and theory and all that. That's an entirely different conversation. But at a very high level, activation functions are used to introduce nonlinearity. Just remember, in a neural network setup, activation is a default feature. So whenever you are using any neural network, the hidden layers, you will by default use something called a ReLU activation, which means again at every neuron, you are doing this computation and you are performing an additional computation with an activation. This is the ReLU activation you're doing. So this is the high level idea of to what's going on behind the scenes. Okay. Yeah. This okay. This is a very simple example we discussed with respect to regression. And now we will discuss a very simple example with classification. We'll understand how the network changes and how some of the concepts change with respect to classification. And now we'll see a small scenario where we'll apply and use neural networks in the context of classification. So that is what we will see. And one of the data sets that we will take up for this leg of the demo would be a very interesting data set called the MNIST data set. It is a digit recognition data set that we will take up for this particular demonstration. And what I want to do first is to show you what type of data we have here. So let me Google out and show you. So this is basically a digit recognition data set. The context of the data set is we have lots and lots of handwritten digits. Okay, so these are lots and lots of handwritten digits we have from 0 to 9. So people wrote lots and lots of digits from 0 to 9. And the objective is to build a machine learning model to identify these digits. And next time anybody writes a similar digit, the model should be able to classify, is it 0, is it 1, or is it 9? So if you understand this a bit more deeply, we have an input image, which is the X. The X here is the picture, the image, which is basically that of the digit. So we have the input image, which is, the input X. And based on that, we are trying to predict the output Y, which is the label. So the input image is the drawings that you see on the screen. These are actually the drawings, which are nothing but pixel values. That's the picture. And based on the picture, you're trying to predict what label is it? Is it a 0 label? Is it a 1 label? Is it a 2 label? Or is it a 9 label? So this is the classification that we are trying to do here. Now, let's understand this a little bit more in detail. How machines see pictures. Sometime back, we already discussed that. We already talked about this very briefly. So let's get a little bit more, little deeper into how machines exactly process images. Now we'll open up this diagram to show you in a better way. You can see this is a normalized and scaled representation that we are seeing. So wherever the pixel values are 0, the digit is actually not present. I think this is a better demonstration. Look at this one. Yes, this seems to be a better demonstration. We are looking at the picture 1, or let's look at this one. This seems to be a better demonstration. Okay, just trying to show you a better image to understand this in a better way. I think this seems to be a better demonstration. Look at this one, all of you. Yes, look at this. So we are looking at the picture 5, and the number 5 can be represented on the basis of its pixel intensity values, right? So we are trying to represent the number 5 on the basis of its pixel intensity values, which are ranging all the way from 0 to 255. Okay, so 0 to 255 is the range of the pixel intensity values. So if the pixels are 0, that means the digit is not present. 0 pixel means the digit is not present. And pixel 255 means the digit is very strongly present. So here, if you see, we are looking at a 28 cross 28 picture. The dimensions are 28 cross 28. So if you look at the width and height of the picture, we have 28 cross 28 image. That means there are total 784 pixels. So how many overall number of pixels are we able to see? There are total 784 pixels that we have right now. And each of the pixels, each and every pixel will take a value which ranges from 0 to 255. 0 to 255. This is how we look at the value of each and every pixel. If the pixel values are equal to 0, that means the digit is not present. The pixels are absent here. So pixel value equal to 0 means the digit is absent here. That is what we mean by pixel 0. Pixel 0 means the digit is absent. And if the pixel value is close to 255, that means the digit is present. Okay. If the pixel value is 0, that means the digit is absent. We do not have a digit. And if the pixel value is close to 255, that means the digit is strongly present. There is a very strong presence of the digit around these areas. And that's the inference we are able to make out. You can see that here it is 255, 255, 253. But as you go to the border areas, it's like 190, 180, 170, 96. It's like grayish. That's the way how images can be displayed. And here you are seeing a grayscale picture. Grayscale image means there is only a single channel. Either it is present or it is absent. And you kind of, you're in middle, like you're going from, it's a grayscale. So either it's black and you go to white. And that's what we call a grayscale. But it could be a colored image also. The only difference in a colored image is we have 3 channels. We have a red channel, we have a green channel, we have a blue channel. So the only difference would be that when we deal with a color picture, you are trying to understand the pixel intensity values for each and every individual channel. So there you will study what are the pixel values for the red channel, what are the pixel values for the green channel, and what are the pixel values for the blue channel. So you'll try to study the individual pixel intensity values for each of the individual channels. For the red channel, what are the pixel values? For the green channel, what are the pixel values? And for the red channel, what are the pixel values? You'll try to understand the pixel values for each and every individual channel. That's the way how we work it out. So anyways, this is the demonstration. This is how the data is, and just wanted to clarify that. So now coming to the solutioning. So you can see this is how we will initially load our data. And here also, we do not have to take it separately. We already have the data set which is available in tf.keras. And just to show you the shape of our data, you can see. So we have 60,000 images, and every image is 28 cross 28. Okay, this is the same picture that I showed you a while back. Okay, so we have 60,000 pictures, and each picture that we have is 28 cross 28. Okay, so that's the inference we are able to make out. I wanted to take a minute and maybe give you another, beautiful depiction as to what is going on uh, in terms of these pixels. So if I draw a number, let's say number 5, so naturally this is in Paint, right? So I can save it in a JPG file or a PNG file, and we call it an image. But if you take any image, you can quite literally zoom into the picture. See, right now we are looking at close to 1 million pixels, right? So I can actually zoom into any image. And if you start zooming into the pictures, you will start to see those pixels come to light. Can you see? You see those very small, small square boxes that are appearing. And that's the intensity value that we are discussing. So this is just to kind of further clarify how machines inherently see pictures, see pictures. Now here again, it's a grayscale image. So we are going from a scale of white to a scale of black. We call it grayscale. Similarly, it can be RGB. So if it's a colored picture, we will have 3 channels. So we will look at the intensity value of the red channel, the intensity value of the green channel, and the intensity value of the blue channel. So when we deal with colored images, you will get a further clarity how that's happening. Okay, so this is to clarify again how machines inherently see pictures. So back to the hands-on depiction again, 60,000 pictures and every image is 28 cross 28. So that's what we are able to see. And just to show you a small depiction of a sample data, you can see this is how sample data looks like. I think here you're able to very beautifully see the depiction is a number 4. So the pixels are very strongly present here, and wherever the pixels are absent, there is no digit that is present. You're very clearly able to see it's actually 4. So what this is the input X, and what is the output Y? What is it exactly? This is actually a 4. So if you try to go and see the output, the class, the label is actually 4. Okay, moving on, let's come to the implementation. So we'll come to the graph in Keras now, and the same way we will build a sequential model. So iteration 1, what I will do, I will remove all the dense layers. I will only keep an input layer and an output layer. 2 important changes we are able to see, right? Everything else is very similar. Nothing is different. 2 important changes. Number 1, we have to flatten our data, right? Point number 1, we will have to flatten our data. If you look at the original input image, the original input is 28 cross 28. Okay. The original input that you see on the screen is 28 cross 28. We have a 28 cross 28 picture. That's the original input that we are able to see. So we cannot directly work with a 2-dimensional image, especially the dense layers that we are discussing, that we are starting our conversation with. They don't work with a 2 dimensions. So we have to convert it to a single dimension, a 1D array. And that is what we do using reshape or flatten. So we are flattening that to 784 pixels. So you can see this, if you do 28 square, you get 784. So simple, we're just reshaping and adding a reshape layer. Second important thing that we added here is activation equal to softmax. Now, this is something that we do for a classification problem. So what the softmax activation will do is, it will convert the output values into probabilities. We did not have to do it for the regression problem. If you remember, for the regression Boston housing dataset, we only added intermediate level activations. And as I said, activations are a standard feature in deep learning. Every layer you will add activation, and ReLU is a very default activation in the intermediate layers. Okay. In the output layer, if it's a regression problem, you can opt to skip the activation. That's what we did for the Boston housing. We did not use activation. Or there are ways where we will use sigmoid activation, other activations, but generally we don't need activations. Okay, because you are trying to predict a number. If you look at the neuron computation, y equal to wx plus b, that is the computation that is happening in a neuron, right? So you don't need activations. You just need a numeric output. Anyways, you're getting a numeric output at the end of the process. That's the idea. That's the core idea. Now, when you come to classification, when you look at this exercise particularly, because that's what we are discussing, right? Let's get the conversation back here. So the output layer, what will happen? You will again predict a number, right? Because the output, neuron output is always y equal to wx plus b, whatever number of features and w1x1, w2x2, whatever. But the general notation is some weight into input plus bias, weight wx plus b. So the output that you end up getting will be a number. Softmax is a way to convert this to a probability. And if you want to get a little deeper into the mathematics, and again, I've given you all the references all the references, but you don't need to get into so much of formula, but the references are here. If it is a binary classification problem, and we'll see a use case of this also. I'll show you all the practical hands-on use cases. If it's a binary classification, you will typically use a sigmoid activation function. Okay, what will the sigmoid activation function mathematically do? What will it mathematically do? It will take the output y and it will convert that output y to a probability. So let's say the intermediate output that the neuron is giving is y equal to wx plus b. Okay, so you have the input x's, and based on that you're predicting the output y. So the intermediate output that is that you're getting is y equal to wx plus b. That's the intermediate output that you're getting. So all you do is you plug it into an equation, and you're effectively getting the probability of y. That's what the sigmoid activation will do. So sigmoid activation will try to convert that y into a probability. That is what the sigmoid activation will do. 1 by 1 plus e to the power minus y. So from the output y, you are trying to create a probability of y. Okay, what is the softmax going to do? The one that we are using for our current exercise? Softmax will do this, friends. Okay, so see, this is the exact use case that we are working on. As I told you, we will have dense of 10. I think that part is sorted because we need to have 10 outputs, because there are 10 classes we have, right? So y0, y1, y2, y3 up to y9. So unlike for the Boston housing, here we will have dense of 10 because we need to predict 10 outputs. The output layer, we need 10 neurons. So dense of 10 is sorted. The only thing is the neurons will predict numbers. The computation of a neuron, the way it works out, will inherently predict numbers. Y equal to wx plus b will give you numbers. Softmax will convert those into probabilities. So from y0, we will have p0. From y1, we will get probability of 1. From y2, we'll get probability of 2. From y9, we'll get probability of 9. So we'll end up getting 10 different probability values such that the sum of the probabilities will be equal to 100%. That is what softmax will do behind the scenes. Okay, it will convert each of those outputs into probability values such that the sum of the probabilities will be equal to 100%. So if you look at p of 0, p of 1, p of 2, and if you add all these individual probability values, you will get something close to 100%. And this is the mathematical computation that is happening in softmax, and it is used for multi-class classification. Just keep in mind one thing. If you're having binary, you will use sigmoid. If you're having multi-class, you will use softmax. And this is only for the output layer. Intermediate layer, what is the activation? You will always use RAID. Okay, so this is e to the power y by summation e to the power y. And if we have to relate it to a use case here, this is exactly how the computation is playing out. So I've taken the example with respect to 3 classes. You can extend it to 9, 10 classes also. But for 3 classes, this is what it looks like. So intermediate layer, we have y1, y2, y3, the output layer. And from that, you're getting the probabilities. So from y1, you're calculating p of y1. From y2, you're calculating probability of y2. And from y3, you're calculating probability of y3. So from the intermediate layers, you're getting the probability values. These are the probability values that we're getting from the intermediate layers. And this is how the probabilities are computed. So p of y1 is e to the power y1 by summation of e to the power y. What is p y2? E to the power y2 by summation of e to the power y. And what is p of y3? E to the power y3 by summation of e to the power y. So that's how we can compute the individual probability values for those respective classes. Okay, so we can compute and you can also see that the probabilities will be computed in such a way that the total of the probabilities will be equal to 100. Okay, so that's the other hallmark of softmax activation. The code is very simple, but I just wanted to take some time to take you through the theory so that you relate to it. Okay, but as I say, this is not needed. It's not mandatory to know all this, but I've given all the references. The theory is extremely deep in deep learning, not needed, but the hands-on is very straightforward because Keras makes it very easy. So because we are using the Keras framework primarily, So TensorFlow Keras makes it very easy to implement the seemingly very complex mathematical ideas in a few 1 or 2 lines of code. So you can see here, if I want to implement all that, so I just need to say activation softmax, and this entire thing will get done behind the scenes. Okay, back to the model summary. 784 input neurons, 10 outputs. We are sorted on this, and rest, nothing much to talk about. The only other additional thing I've done here is, you can see loss function is categorical cross entropy. This is something you need to memorize. There's not much to talk about. This is the typical loss function that we use for classification problem. And one more thing that we have done is we have adjusted the learning rate. Unlike the last exercise where I took a default learning rate, here I actually used a specific learning rate of 0.1. Okay, so I'm using optimizer and I'm specifically setting a learning rate. That's it. So this is the model compilation. And now we can execute the graph. Remember, I have not added any hidden layers. I've only added input layer, output layer. And you can start to see the accuracy of the model. This is the training accuracy that is getting computed. And after the epoch is completed, we can see the validation accuracy. So we can get a very nice idea of the progress of the network, how the network is training as it goes through multiple epochs, as the weights and biases of the neurons are getting adjusted. We can beautifully see how the network is learning, how the network is progressing. So what is the training accuracy? You can see as the number of epochs are increasing, the training accuracy seems to increase and the validation is also increasing. So this is a good sign. It's a good sign that yes, maybe my network is learning. Okay, and this we need to monitor. But I think you can see it's stagnating. It's not, I mean, the increments are not that strong. It's not that high. And most likely the reason why this is happening is because we have just used the same, a basic artificial neuron. We have not actually, used it in layers. So what we have done here is not exactly deep learning. It isn't a neural network I have used. I've just used a single, neuron, if you see, because we just use input layer and output layer. That's it, no hidden layers. Okay. So next iteration, what I will do, I will add a hidden layer, and you will see a monumental improvement and a monumental change in the accuracies. You will see a drastic change how the accuracies will change the moment I add some hidden layers. Okay. So let me go back now. In the next iteration, I will add a few hidden layers and show you the magic that happens. So I already had these layers. I removed it. See, in hidden layers, we always use ReLU activation, and the output layer is softmax activation for classification. Okay, these are some standard best practices that I'm sharing with you. Okay, so now I'll train the model again. If you see, I just changed the architecture, recompiled, and I'm doing a model.fit. And you will see a drastic improvement. In the first epoch, it's a little slower. It's a little slower because there is more computation happening. In the first epoch itself, look at it, we strike jackpot. We are already up to 95% validation. Let's wait for the second epoch to complete. The training accuracy seems to be increasing drastically. The learning is really strong. We are touching 96.85% accuracy. So this is the difference that deep learning brings to the table. So by adding those hidden layers, we are able to build a much better model than what we had before. Okay, so all of you are able to see what we got here. So these are the yeah. So we can keep training for 10 epochs. And this is the incremental improvement we are trying to see. We see that as we increase the number of epochs, the training score is also improving. The validation score is also improving. So you can see it's touching 97.79. But beyond the point, it will stagnate. After a point, if you continue doing this, it will stagnate. And for that, we have to learn a different network. We'll discuss that later. So we will use CNNs and convolutional neural networks to work with it in tomorrow's session. So today, until now, we will just use a dense layer. But this is exactly, you can see after a point, what's happening is there seems to be a kind of an overfitting tendency, right? Maybe a couple more epochs will give a better idea. So after a while, what is happening is, mostly the training score will continue improving. That will always happen. If it's a powerful network, a deep network, the training accuracy will always increase. But if it overfits, the testing will tend to come down. It will first stagnate, and after that, it will tend to come down. Okay, so we can just wait for 10 epochs and see the pattern. But still, I'm sure you agree it's a drastic improvement from what we had before. So the training score seemed to really increase. It's gone up to 99. But you can see despite the training going up, I think it's already starting to show signs of overfitting. It's fluctuating a little, but we can see the validation score is not really improving. It's either stagnant or it's kind of, reducing. So the training is going up, it's continuing to go up, which is expected. But let's see the validation for the next epoch. You can see the validation has sharply dropped. So we are seeing a tendency of overfitting, right? Very clearly. And this is expected because we have a very powerful architecture. We have a very deep architecture. We're already up to 185,000 parameters here. And you can see that it's the training score is continuing to improve, is continuing to increase. And as the epochs progress, the testing seems to either stagnate or come down. Okay, so this is the thing that we are able to see right now. It's a very basic classification exercise that I wanted to share with you, so that all of you. So a lot of learnings, a lot of new learnings in this exercise. We understood about pictures. We understood how machines perceive pictures. What are pixel intensity values? We understood about activation functions. We saw what are some activation functions, best practice activation functions that are used. So all of those kinds of things we saw. And the other core ideas remain the same. So model.fit is the part where you're training the model. And if you want to do the prediction, you will use something called model.predict. So model.predict is what you can use for the prediction. So you can see that if I have a new picture, I can simply say model.predict. And remember, when I use the predict function, what will happen? I will end up getting 10 different probability values. Okay. So when I use a predict function, I will end up getting 10 different probability values. And out of those 10 different probability values, we want to find out which one is the highest. Okay, so when we use model.predict, we will get 10 different probability values. And out of 10 different probability values, we'll try to find out which probability is the highest. So that is the digit that we use. So whichever probability is the highest, that's the output class. That's the way how we work it out. So you can see this is a sample picture I'm taking. So I'm giving this input as this is the input we are giving, and we are using the network to predict what is that picture, and the network has predicted 2, and actual is also 2. You can see that it's really the 2 picture. Okay. I wanted to just show you one more very interesting concept here with respect to the learning rate, because remember I took a learning rate, but I did not quite demonstrate to you what the learning rate is doing. So what I will do in the next iteration is I will keep the same architecture, but I will just initialize from the beginning again, so that the same weights and biases are not getting used. Let me reinitialize the network, and only thing that I will do now is observe this, all of you. I will reduce the learning rate a lot. Remember, I have kept every other thing the same. The only thing I have done is I have reduced my learning rate a lot. Now, what it will do is the network will still learn. You will see that it will still learn, but it will take a long time for the accuracies to pick up. Can you see how the training accuracy is really starting low? It will take a long time to train. Okay, so you see it's 10.63, 6.59. It will improve. The training and validation scores both will improve. It will eventually still reach 96, 97% zone, but it will take a long time to improve. So you can see it's still improving. Yes, 13%, 17%. Network is becoming better, but it will take a long time to improve. This is just another concept I wanted to clarify. So how you can tweak the learning rate. This is the hyperparameter. So as you train a neural network, you need to monitor your learning rates. You need to choose the right value. If you see the training is going this slow, you try to improve the learning rate. Okay, so these are some other things to keep in mind. Okay, so next iteration, what we can also do is show you another extreme. Another extreme is what if you have a very high learning rate, right? So typically you should not have it, but what if you have a learning rate of 3? If you take a very high learning rate, like you can see, for example, it is not callable actually. So anyway, so don't take a learning rate that is this high. Okay, usually you should never take a learning rate that is so high. You should always take a learning rate which is typically in a smaller range usually, right? So the learning rate should be less. Okay, so you should take a learning rate which is small. So you should not take a learning rate that is very 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 large. Here I'm taking a learning rate which is like 0.9. So even if I take a very high learning rate, it's a problem. Can you see? So there were two extremes. Extreme number one was we took a very small learning rate. If I take a very high learning rate, the network will find it very hard to learn. The losses will remain high. I'll show you. I'll show you. I mean, so you can see that, training it for, let's say, 10 epochs, you can see the pattern. Even if you take a lower learning rate, it's still okay, because you will still see a sign that the network is learning. But if you take a very high learning rate, it will continue. It will continue at the top. Rather, the accuracy is dropping. You see, it's finding it very hard to learn, because the weights and biases are changing so drastically that it's finding it very hard to learn. See, the validation has actually dropped. This is even worse, right? So having a very high learning rate is worse. Never have a learning rate more than 0.1. Either is 0.1 or lower than that. So don't take a learning rate that's this high. Okay, these are some of the ways in which you learn different things. So try to see different things in action. Try to learn from best practices, right? Because just like how we have done machine learning for all these days, deep learning is also a highly experimental domain, the highly empirical domain, if I have to use that right term, where you find out and you work with best practices. There is not always will you find a mathematical evidence that, okay, this will certainly work, this is why it works and all that. There's no equations or formulas you will always find, but it's just that you see a book, you see an article, uh, somebody says this is how it is, and you have to accept it, right? So people have seen that, okay, keeping a high learning rate doesn't work. So we have seen this in our experience from by training networks, and all the books and best practices suggest that. So this is something that you will see. So no matter what network you take a high learning rate, you will see the learning will not happen. Okay, yeah, all right. Because, and this is in my folder, so I'm going to just take it back to how it was, take it back to 0.1. I'll see. I'm keeping the rest of the stuff exactly the same. Nothing I'm changing. Just by reducing the learning rate to 0.1, my accuracy instantly spring up. See the magic? This is the magic. Sometimes it can be very frustrating. When you're learning these topics from scratch, it can be very frustrating. So you take a learning rate and you're wondering, hey, what happened? Like, why is my loss not reducing? Most likely, 9 out of 10 times, or some, I'm 9 out of 10 times, the issue will be learning rate. If at all you see the learning rate is, the accuracies are not improving and something, 9 out of 10 times the issue is learning rate. Reduce the learning rate and instantly you will see the network will start to train. Okay, so this is once again a very, very important best practice to keep in mind. So now we will do some exercises. I will, based on the ideas that we have covered, we have discussed one use case with respect to regression. We have discussed one use case with respect to classification. So we will do a few exercises. But before that, I wanted to also share with you a couple of other characteristics of a neural network. Let me take a moment to also share with you a couple of other characteristics of a neural network. And one of the things that I've done, I think this training is almost complete. You can see 6 out of 10. So this is okay. Let it go on. What I've done is I've actually gone and highlighted this in a small slide. You can look at the last one, which talks about all the important components that you have in a uh, that you typically have in a neural network, right? These are all the different components that you have. Okay, these are all the different components that you have, friends. The first one is number of iterations. This is the number of epochs. I think we are sorted on this. We understand what is epochs because uh, the more the number of epochs, the more gradient descent is happening. This is the part where you're tuning the weights and biases, W's and B's. I think we are sorted on that, epochs and iterations. Next one is batch size, very important. We haven't used it yet in detail, but batch size is an important concept because what happens is when you're working with real data, data can be huge, right? Especially when you're working with high resolution images and all that. Some of that data can be really big. And imagine if you are working with images, each and every picture can be 10 MB. 10 MB isn't a big size, right? So one picture that you, one photo that you click from your smartphone, 10 MB in size. And if you just take 100 images, you do the math right now. If you just do 100 images, 100 into 10 is 1000 MB, 1 GB. And 100 images is a very small number, right? If you take it up to 1000 images, every image is 10 MB, you're already occupying 10 GB of RAM. Because remember, you need to store all the pictures in RAM or in your main memory for it to process. So whatever we are doing in Collab, if at all we work with real image data, which I'll show some computer vision use cases tomorrow. Uh, you will start to see that it becomes unmanageable. It becomes literally unmanageable because even to load the data, because then we will not be loading CSV files, we will be loading real pictures. If you just want to load 1000 pictures in memory, or in this case, the Collab RAM, you would already have occupied 10 GB of RAM. And 1000 images is a very small number I'm taking. Real world use cases, you will be dealing with 20,000, 100,000 pictures. Do the math right now, 100,000 pictures, each picture is 10 MB. You don't even find a RAM that's big enough like that, no? So this is why it is a very important practice to split your data in batches. Whenever you're doing deep learning, particularly, because in deep learning, you will be dealing with unstructured data, and especially unstructured data can be very, very big in size. Pictures, images, audio, video, text, right? So they can be huge in size. Videos, particularly, videos are massive, right? And videos are no different from images. They're frames, they're image frames, right? So the same way that we have a picture, a video is nothing but a frame of many, it's like a combination of many, many pictures. So if I let's just say 30 frames per second, so in a second we have 30 images. So you'll process videos the same way that you process pictures, but videos can be huge. One video sequence can be like 1 GB, right? Think about it. If you're looking at surveillance feeds or surveillance images and trying to do some object detection based on that, imagine the amount of compute that will be needed, right? So in real world scenario, you must split your data in batches, smaller batches, 16, size of 16, size of 32. So take 100 images and process them in batches of 8, process them in batches of 16. Otherwise, you will go out of memory. We talked about learning rate. I think learning rate is sorted. We understand learning rate typically a default 0.1, 0.01, lesser than that. Take a lower learning rate. Always it's a good practice to take a lower learning rate. So we talked about that. Two other very important things are number of hidden layers and number of hidden neurons. How many neurons we have in each layer. These are both hyperparameters. You will have to experiment. You will have to try out different permutation combinations and see what works. We tried to give you some examples here in this discussion where I showed you a very basic network where I am not using any hidden layer. And then iteration 2, I showed you a network where I'm using 3 to 4 hidden layers. And you can also experiment. But please be mindful that if you add too many hidden layers, if you had too many hidden features, then your network might become prone to overfitting. So please be mindful of that. If there are too many features you add, then you might end up getting something called overfitting. Okay. Then we talked about activation functions, and another very interesting thing is called dropout. Dropout is something I haven't discussed yet. Neither have we seen the code for that. But what is the concept of dropout? Dropout is a kind of a regularization technique. Okay. So dropout says that, let's say in every dense layer, every hidden layer, you can specify a certain dropout percentage. Let's say if I set a dropout percentage of 0.3, what it means is I will randomly drop 30% of the neurons in that layer. That is what dropout will do behind the scenes for you. So every hidden layer, you can specify a dropout percentage. After every layer in Keras, you can say, okay, dropout of 0.3, dropout of 0.4. And what it will do, it will randomly drop that many percentage of neurons from that layer. And in case you're wondering, okay, why do we do that? Why will we ever want to remove neurons? Because you want to prevent overfitting from happening. Okay, so some of these architectures can be so deep. Some of these deep learning architectures can be so complex. You can end up having hundreds of hidden layers, several tens of thousands or hundreds of millions of neurons. If you add up across the layers, you will easily get up to hundreds and thousands of neurons, which is very common. And it is very easy for the network to get overfit. right? Overfitting is a very real problem. So on the training data, the network is so powerful, it will learn the patterns perfectly, just like what we were seeing for Boston housing, isn't it? You are already see, or maybe the MNIST data set, you already saw that. After a point, when I keep training over multiple epochs, the network is so powerful that it will try to learn those patterns perfectly. So how do you prevent that from happening? The way to prevent that from happening is you can use a dropout. You can use a dropout regularization to ensure that even if you have 100 neurons in a particular hidden layer, but you will not use all the 100 neurons. You will only use 40% of the, you will only use 60% of the neurons. So 40% of that will drop typically. That is the basic concept behind dropout. So we will not be dropping all the, uh, using all the neurons, but we will only be using 60% of the neurons. So the remaining 40% we will basically drop. That is the core idea behind dropout. And in a way, it's a way to, I would say, prevent overfitting from happening. Okay, you're able to, regularize the model and ensure that you're not using all the layers. You're able to kind of prevent overfitting from, from playing out. That's the concept of dropouts. Okay. All right. So that's pretty much what we have here. I hope everyone's understood the core idea, what it is, and so now with this in mind, let's move on. And if you want to see this in action, actually, I wanted to show you in the same demonstration. It's a very basic example, I know, but I mean, if you want to experiment with these ideas, this is the MNIST is actually a gold standard data set. It's a very old data set. It's been around for a long time, but it's an absolute gold standard. If you want to do some experimentation, this is absolutely a gold standard that you can use for doing some kind of experimentation. I can just go and again, in collab, as we especially work with the exercises tomorrow, one of the other things that we have to do is we need to go to runtime, change runtime type, and change it to GPUs. Okay, so it won't be that important today, but especially when we come to computer vision, CNNs, and all that tomorrow, we will have to use GPUs. And Colab gives you free GPU. It is limited. It's not unlimited. There's some limits that Colab will impose, but this is the way you can change it to GPU. Okay, you can go to runtime. You can change runtime type. You can change it to GPU, or you can also use TPU. TPU stands for Tensor Processing Unit. This is specific to TensorFlow. This is from Google. Okay, it's an alternative to GPUs that you can also use. Anyways, nothing in the code will change. It will run the same way. But if you look at your compute, if you look at your runtime, you will see that we have got this GPU RAM that is available. Okay, all right. And this part is very important. Resources are offered free of charge, are not guaranteed. So nobody is guaranteeing resources. So there might be times when it will fail. So you need to be mindful of that. This is only for training, but it's not guaranteed that you're getting. But 16 GB of GPU RAM, who gives you for free? You tell me. Obviously, you have to accept some things, right? So it's a small trade-off. So this is good enough for learning. It's good enough for learning. Colab is one of the most popular collaboration and learning platforms out there globally. Okay, very, very popular actually. So now I'm just going to go and complicate the network a little bit more. And if you want to absolutely make it overfit, what you can do is you can really pack some more punch. Let's see if I can, and this is also like an exercise you can all do. Like you can try to, make the model overfit. So you can try to see, uh, try to define a really, really complex architecture and see if you can go back and make the model overfit. Let's see. And another very good practice is don't try to have huge layers. Like don't try to have dense of 100,000. This is a bad practice. Okay, so try to have deep and shallow, kind of try to have deep layers. So don't try to have like one single hidden layer with lots of neurons. So there's no science, like there's no evidence, there's no mathematical formula that tells you that this is exactly how you need to do it. Like if you want 401 neurons, you can do that. It's up to you. Okay, so it's not like somebody's telling you have to give 400. No, it's just a convention. But these are some general best practices. So never have a dense layer that looks somewhat like this. So always try to break it up. Even if you want to have something like this, break it up. Break it up into two pieces. Like let's say I have a 800, and in the previous I have a 1600. So break it up into two intermediate layers. So see what I did here. I actually created a very complex architecture. I don't need to do it. I don't need to, but I just wanted to show you that how you can easily end up overfitting a model. Okay, if you end up doing something like this, so the number of parameters have absolutely skyrocketed. Can you see 7.69 MB looks small? Okay, but maybe a few changes you can do here and the number of parameters will skyrocket. So let me just try it out. It will be a little slower, but you can try it out how the network is going to train. Okay, let's see. I've compiled and I can run the code over 10 epochs and you can see. You can see. Okay, see the GPU. Look at the impact of GPU. Super fast, right? Straight away you're seeing an improvement happening. Super fast. Look at the magic. You try doing with CPU and without CPU. Look at it, and you can already see the overfitting will happen after a while. So epoch number 3, 97.95, and after a while you will start to clearly see a pattern where the training will continue to increase, but the testing will like it won't increase beyond the point. So you'll find it very hard to increase your test accuracy beyond the point. It's a very clear pattern that you will see. Okay, just wanted to mention this part to all of you here. Okay, so this was a bit of a new learning I wanted to mention to all of you. So runtime, change runtime type GPU. So the training is super fast right now, you can see. So every epoch is completing in less than 5 seconds. It's a good way to compare the runtime. You can see every epoch is approximately 5 seconds, it's 10 seconds. You try with CPU, CPU will be excruciatingly slow. Okay, the same exercise you can do with CPU, without CPU, and you will see the difference. The difference will be massive actually. You can see, yeah. All right, so we'll keep it at this for now. So this was the demo I wanted to show you. Okay, so these are both are very basic demos we have seen. It's not very difficult data sets, pretty academic. So the discussion until now has been very academic. We looked at a Boston housing and an MNIST data set, but one of the most important things we achieved today is we went through the foundations of deep learning. The foundations are clear. Foundations are clear. What is what are the different components of a neural network? And now using those foundations, we will be getting into deeper topics as we go along. Okay, so this is where we will stop for today. I'm going to keep some time for question answers, and then we'll take it forward from there.